Good afternoon. Welcome, Professor Golin, in the international webinar. Yeah. A special thanks to you that you have accepted our invitation. So on behalf of our KIIT University, on behalf of our honorable founder, and on behalf of our School of Applied Sciences, on behalf of organizing committee, and on behalf of me, I heartily welcome you in this 2 days international conference of advanced functional material. So I request Bhaiba Madam to start the chair.
Good afternoon, all of you. I welcome all the participants in the AFM 2020. So I welcome Professor Guilin Pauline Vitrent for her talk. Professor Vitrent is full-time CNRS researcher at University of Tours, France. She obtained a PhD in electrical engineering in 2004 from Paris University, France. Her research interests are experimental investigation and theoretical model development for piezoelectric materials and devices. For various applications, actuators, for flapping wing micro air vehicles, piezoelectric transformers, piezo semiconducting nanowires for mechanical energy harvesting. Currently, her projects are focused on mechanical energy harvesting using piezoelectric materials like flexible nanogenerators based on piezo semiconducting nanowires or cantilever type piezoelectric generators including piezo ceramic films. She co-authored 39 publications in international journals and given many invited lectures in international conferences. So I welcome Dr. Guilin Pauline Vitrent, and I invite her to start her talk.
Thank you very much, and good afternoon, everyone. Thank you for inviting me to this very interesting conference. And I will start my presentation and I will start sharing it. I hope it will work as soon as possible. Okay, so normally I will put in full screen. You can see it? Yes?
Yes, Professor.
Okay, thank you. So before presenting my research project, I will just give you an overview of Gréement Laboratory, which is a research group on materials, microelectronics, acoustics, and nanotechnology. So this laboratory is located in France, in the Loire Valley, and in the center of France. We are approximately 110 members. Among them, more than 50 researchers or teachers, researchers, and 20 technical and administration staff, and 20 PhD students and 15 postdocs, approximately, and also 8 scientists associated to our lab. The targeted applications of the lab concern production, transport, storage, and conversion of electrical energy, but also embedded electronics and energy harvesting. And finally, measurements, control, and diagnostics for industry and medicine, in particular with ultrasounds. What is the politics of research of Gréement is to work in order to get some more integrated, high performance and clean energy efficient devices. This is why we have skills and knowledge in terms of new materials, design of dedicated devices, and also strategies of energy management in order to harvest energy or to convert properly this energy. And the lab is organized in 4 teams. The first one is the team called New Functional Oxides for Energy Efficiency. So the idea is to synthesize and shape oxides, targeting properties leading to a high energy efficiency, and many different types of materials are studied: crystals, thin layers, massive ceramics, nanopowders, nanowires. And we have several operations of research. I won't detail them much today, but you can go to the website to see this more in detail. And currently the website is being modified, being updated, but in a few weeks you will have a lot of details on these different actions. The second team is called Magnetic and Optical Properties of Ferric Materials and materials with high correlation. My colleagues are doing some optical and Raman spectroscopy, but also numerical simulation in order to better understand the microscopic mechanisms leading to electrical and magnetic properties. Also, several operations of research are defined and are the following. Team 3 is called DISCUS. It means Ultrasonics Devices and Characterization. And it is dedicated to develop new acoustic microsystems and to do the study as well as theoretical and experimental, and to conceive, to design these ultrasonic devices, but also to use them in order to characterize complex environments. 3 operations of research are dedicated to piezo materials, but also ultrasonic transducers and sensors, and ultrasounds used to analyze complex media. The next team I am part of, it's ECOSYM, Energy Devices, Systems and Microelectronics. And we work on the development of new devices for our future needs in power and mobile electronics. So we are dealing with porous semiconductors, silicon, porous silicon, wide bandgap materials and devices, MEMS or NEMS from design to characterization, and finally, complete systems of conversion of energy. The works I will present today are included in this operation of research dealing with MEMS and NEMS. And I will now detail them a little more. And my talk is dedicated to low temperature synthesized zinc oxide nanostructures and their integration into nanosystems. All these works were possible thanks to a full team. So my colleagues, Daniel Alquier, Camille Justo, Kevin Nadeau, Taufik Tlemkani. And I will give some more details now. First, I will talk about the general context. Then I will give you an overview of piezoelectric nanogenerators incorporating zinc oxide nanowires. My third part will be dedicated to zinc oxide nanostructures integrated into field effect transistors. And then I will give some conclusions and perspectives. First, the context. Why do we perform energy harvesting? Why do we intend to do that? It's in order to supply wireless sensor nodes. You all have already heard about Internet of Things. This new world, connected world, is possible only thanks to small devices integrated, which are doing some sensing and communicating with the external environment. To work properly and to be able to communicate and to sense, we need energy. And non-rechargeable batteries are not the best solution because of the need of replace, recharge, and the pollution which is possible if these devices are let in the environment after use. So we are targeting to supply them with renewable energy from the environment. And you can see here some example of consumption of targeted devices like radio frequency emitters and transceivers. And you can see that the consumption of these devices decreased a lot since a few years. So we will target the following power range below 100 microwatts, perhaps 1 milliwatt, not more. And we, in terms of energy range, it's in the order of 100 of microjoules. Historically, about piezoelectric nanogenerators based on zinc oxide nanowires, Zhongli Wang's team at Georgia Tech proposed the first proof of concept in 2006 with this interesting experiment using an AFM chip. Since then, different devices were proposed, improved, and the last one is a polymer nanowire composite composed of zinc oxide nanowires and an embedding matrix. I will give you some reasons why we use this matrix. So I will detail this part. We are doing such piezoelectric nanogenerators at Grémont. And first I will present you the principle of hydrothermal synthesis of zinc oxide nanowires. Then the full steps of a process of nanogenerators, their functional characterization, and some key issues to improve their efficiency. So how do we exploit these piezo semiconducting nanostructures? We have two ways of mechanical excitation. It can be a transverse force or a longitudinal one. And here you have the distributions of potential, of piezo potential appearing when you are compressing or bending such a nanowire. It is embedded in a polymer matrix, insulating one. And this matrix is introducing a capacitive coupling, which means that we can access to a difference of potential on both electrodes of the device. What are the main reasons of using zinc oxide nanowires or other piezo semiconducting material nanowires? Nanowires don't fracture easily. If one is failing, it doesn't compromise the operation of the full device. It's working far below the natural resonance frequency of the nanowires. It means that we can work in a quasi-static way at the point of view of the nanowires. So they will work identically on a wide range of frequencies, which is quite low. And what is interesting is higher sensitivity compared to bulk zinc oxide. You can see here some examples of piezo coefficients determined experimentally in literature. Zinc oxide is biocompatible, which means also a huge number of applications in medicine. We are working on all the aspects of the chain at Gréement. We are doing zinc oxide nanowire synthesis and full device manufacturing. We are modeling thanks to analytical tools or finite elements modeling. And we are also doing some characterization, structural, but also electrical, to determine in particular the doping level of the device, of the nanowires. And we are doing some functional characterization of the full device. Hydrothermal synthesis is a quite easy way to get some well-aligned and nanowires with a good crystallinity. You can see here a same image of such nanowires. The reactants are zinc nitrate hexahydrate, HMTA, and sometimes ammonia, which can have some interest. We put all of this in an autoclave in an oven, and we heat it at relatively low temperature. It means below 100 degrees. It's compatible with industrial processes, and it's also compatible with flexible substrates like plastics. The major limitation of this type of synthesis is the high level of defects in material that we obtain, and we will talk about it more in the following slides. Here you can see the lengths of the nanowires against time. So it's not worth letting the process, the synthesis during tens of hours, because the lack of reactants will decrease the reaction. So only a few hours is enough to get nanowires with 1 micrometer length. Here are the nanogenerator process flow steps. And you can see here the different constituents of this device. A substrate, a bottom electrode, here it's gold directly, some nanowires well aligned, the deposition of insulating matrix in order to give some robustness, mechanical robustness to the device, but also to prevent the nanowires to touch themselves and to prevent some internal discharge of the produced charge, and the discharge internally to the device is not good for supplying external devices, of course. Third step, the deposition of the top electrode and then wire bonding. This is a picture of rigid nanogenerators on silicon substrates. And here, flexible ones we did on PET or on PDMS substrates. Here you have a cross-section showing the lengths and the different thicknesses. In particular, the isolating matrix is in parylene C, deposited by CVD method. And the residual thickness of parylene C over the nanowires is quite small, 300 nanometers approximately, smaller than the length of the nanowires themselves. It's important in order to have a good electromechanical conversion. We also developed a new method of production of flexible and stretchable devices on PDMS substrates. Here you have the different steps with a last step, which is a release of the device from the rigid substrate. And you can get such devices which can be folded, stretched, thanks to the properties of PDMS. How do we test such nanogenerators? We developed a dedicated test bench, fully controlled by a computer. We apply a vertical force thanks to a shaker applying the arm at the top of the nanogenerator, and we measure it thanks to a high input impedance double buffer circuit. It's better to do that than using usual voltage probes whose impedance are modifying greatly the voltage that is measured. And we can control also the value of resistive load connected to the device. You can get such curves of power, delivered power versus resistive load at different frequencies. And you see, of course, that the higher the frequency, the higher the harvested power. We did some tests with increasing compressive force. You can see here the open circuit voltage, showing quite a good sensitivity of this device, 90 millivolts per kilopascal. We checked the durability, which showed good, interesting first results. And of course, we did many studies with when connecting the device on a resistive load. And finally, we manufactured such devices on bank cards to show that larger devices are possible to manufacture. And it makes also possible to apply a force or a pressure on a larger area, like with the hand. You can see here the curves of voltage and current versus load, and the corresponding power with quite interesting maximum voltage measured 35 microwatts at the optimal resistance. This optimal resistance value can be a problem when connecting to external circuits. This must be dealt with a convenient electronic converter connected at the output of the device. We also connected nanogenerators directly with a liquid crystal display, showing that we were able to supply it directly. I will now talk about some key issues in order to improve the performance of these devices. In particular, N-type doping is encountered on these nanowires. Why? It's because some defects are present in these nanowires grown by hydrothermal synthesis. These defects can be oxygen vacancies, zinc interstitial, hydrogen impurities. This is still under discussion in the scientific community, but it leads to a high intrinsic N-type doping at the level of 10 to the power 18. These impurities, these defects, lead to the existence of intermediate energy levels close to the conductive band. And these free charge carriers appearing in the matter, moving in the material, tends to screen the piezo potential and to decrease the piezo potential, like you can see here in this schematic. This is not a good thing for the energy harvesting purpose, of course. This can be also highlighted thanks to finite element method simulation. So you can see here that when the doping of these nanowires increase, the potential, the difference of potential at the extremities of the nanowire tends to decrease up to a few tens of millivolts. How can we measure such doping? At Gréement, we have a lot of experience on transistors, design of transistors for microelectronics. So we prepared some single nanowires field effect transistors. Like here, you can see the schematic. And the nanowire is the channel between source and drain of the transistor. You can see here the same image of this zinc oxide nanowire between source and drain. And we will characterize these transistors, and thanks to voltage current characteristics, we can deduce interesting information regarding the carrier transport type and the carrier concentration and mobility. Here you can see such characteristics, and measuring the threshold voltage, we can deduce the carrier concentration of the device, of the material. This was done on our nanowires, showing that starting from a degenerate semiconductor, when we anneal these nanowires at 350 degrees, we can decrease this doping up to 10 to the power 17. And if we increase again a little more the annealing temperature, we can go down to 10 to the power 16. So a simple thermal annealing in air is a good way to decrease this doping. This is not convenient for flexible substrates, of course. This must be done. These other means must be found to decrease the doping than thermal annealing, and it's under investigation at the lab. Anyway, when decreasing this doping, the nanogenerator's performance is improved by a factor 4, and this was measured on many devices. Another key issue of the design of efficient nanogenerators concerns the surface density of zinc oxide nanowires. And we can remind the theory of 1,3 piezocomposites, which theory was introduced by Professor Newnham a long time ago. And our nanogenerators are like 1,3 piezocomposites. And this structuration in a composite has a lot of interest, because if you measure or if you simulate the electrical energy of our devices for different volume fractions of zinc oxide, you will see that we are a lot over the level of zinc oxide layer, pure zinc oxide layer with the same properties, exactly the same properties of zinc oxide, and the nanostructuration gives such results. This is very interesting, and of course, in ultrasound transducers, the same tendency was also used to improve the performance of ultrasound transducers. How to control the density of our nanowires? Synthesis parameters can be adapted. And in particular, you will see here some same images at different gross temperatures. Here, from 70 degrees to 100 degrees. Also, we can introduce some ammonia during a reaction, and the concentration of ammonia will also change a lot the density of the nanowires, like you can see on this graph. The density tends to increase when you are increasing temperature, and also tends to increase when you are increasing the concentration of ammonia. So more than 3 orders of nanowires density variation can be achieved by these two means. The only problem of introducing too much ammonia in the solution is that it has the effect of increasing the level of defects. As you can see here, the graph versus ammonia concentration, the free charge density in black is increasing. So there must be a compromise between control of the density and not too much level of defects in order not to decrease too much the performance of the device. Single nanowires transistors are not the only way to determine the doping level of semiconducting devices. And photoluminescence spectroscopy is a structural characterization which gives more directly an idea of the doping of the material. This is done in collaboration with University of Catania, with Professor Mirabella. And here you have the curve of intensity of photoluminescence versus energy. And you will see that the level of defects in the material is proportional to the ratio between visible intensity over UV intensity. So you can see on the right side, on the right graph, that this intensity is decreasing when increasing ammonia concentration, showing that the level of defects is increasing. Another characterization method is very interesting. It's electron paramagnetic resonance spectroscopy. Professor Erdem, who presented yesterday a talk in this conference, gave a lot of details on this method and interesting results. And we worked together on zinc oxide nanowires. And these EPR measurements can be used complementarily to PL measurements in order to distinguish the types of defects, because EPR can help to separate core and surface defects of zinc oxide. And we showed that increasing the annealing temperature had the effect of decreasing the concentration of paramagnetic defects. And more precisely, here you have the intensity of signal of EPR spectroscopy. And you have two peaks. One peak is characteristic of surface defects, and another peak is characteristic to core defects. And when annealing our material, nanostructures, we see that the core defects level decrease when increasing temperature annealing, and the surface defects level increase. And there is also a signal shift, which means there may be some contribution of different defects. Here you can see the curve of core defects and surface defects through the concentration of spins obtained thanks to EPR. Going back to the different constitutive parts of the nanogenerator, the seed layer is also very important for the performance of the device. This seed layer is necessary to allow nucleation of the nanowires, and it will have a great influence on the morphology and quality of zinc oxide nanowires. It can also play the role of bottom electrode if it is enough conductive. On the contrary, if it introduces a series resistance, it can decrease the efficiency of the device. It also must be well chosen in order to prevent delamination of the different layers, and it must be compatible with industrial process. We did a study of a zinc oxide seed layer over the gold electrode, the gold bottom electrode. And this is what we observed. When decreasing the thickness of this seed layer, we obtained an increasing density and an increasing alignment of the nanowires. But also, we we saw that when we anneal this zinc oxide seed layer, we got a better arrangement and a better homogeneity of the nanowires compared to non-annealed zinc oxide seed layers. The annealing is performed here at 400 degrees for 30 minutes in air. So the nanowire density increases and you have better alignment of the nanowires when you anneal the seed layer. We also compared 3 different types of seed layers, gold, zinc oxide, and aluminum doped zinc oxide. This is very important because if we could use aluminum doped zinc oxide, we could have in a single layer the electrode and the nucleation layer. Here we have some results of a study done comparing these 3 types of seed layers. And what is interesting to see is that the best alignment and homogeneity of the nanowires was obtained on aluminum doped zinc oxide, azo, compared to zinc oxide seed layers and gold seed layer, who gave here quite low and poor density of nanowires. So we can think that this azo seed layer will give the best performance on the final devices. But these azo layers introduced a series resistance, which means that the power was not as high as the zinc oxide seed layer devices, which means that further development is necessary and is ongoing at the lab. As a conclusion on this nanogenerator part, we showed that we could harvest levels of 30 microwatts of power thanks to our devices, and we could supply some small power electronics. And we will keep going on the control of n-type doping of these layers, of these nanowires, and performing also aging tests more deeply in the future. I will continue. I don't know if I have a lot of time, not much. I will continue shortly with zinc oxide nanostructures-based field effect transistors. These transistors were done in order to determine the doping of the nanowires. Here you have the schematic of a transistor. And here, so a transistor with zinc oxide nanowire as the channel between source and drain. Ideally, we have such characteristics for platinum zinc oxide contact with abrupt current saturation with voltage. In our devices, first we obtain such characteristics showing no rectifying behavior, no FET current modulation due to high charge carrier density. After annealing in ambient air at 450 degrees, we obtained very interesting behavior of our transistors. And you can see here, we have a modulation with gate voltage in this output curve. And we obtained very good performance with low off-state currents, high on-state current, steep subthreshold swing, and a good field effect carrier mobility. We also worked on other types of nanostructures, I mean zinc oxide nanosheets, obtained this time by VLS method, vapor liquid solid method. You can see here same views of these zinc oxide nanosheets with a very good crystallinity. These sheets were used to perform some flexible field effect transistors on flexible substrates with pyrrolene as a material chosen for the gate dielectric. It gave a good interest. Pyrrolene was able to cover conformally the nanosheets and to give a large capacitance per unit area. And pyrrolene is transparent. Here you have the characteristics showing a good behavior of the transistors, a negligible hysteresis. And we can do this for also, we can imagine such devices with multiple channels, with multiple nanosheets, in order to increase the on current. This was done on flexible substrates, and you can see here different zinc oxide nanosheets in parallel. How do we do this? We don't do dielectrophoretic alignment, we do mechanical shear force by making shear and bend the nanowires on the gross substrates to have them parallel to the substrates. Finally, some interesting, another type of transistor is very promising, is the source-gated transistors, SGT. This type of transistors appeared in the early 2000 years. It's interesting for low power electronics, and we studied them in collaboration with University of Surrey. The device feature is the source contact is Schottky, and so the transport is controlled at the metal semiconductor contact. How did you? So we manufactured such SGT with our zinc oxide nanosheets, and we obtained very good performance of these devices with very early drain current saturation and a high gain compared to classical FET, zinc oxide nanosheets FET. Here you have a table comparing the characteristics of both types of transistors. And the SGT show on current uniformity, which is very interesting compared to FETs. As a conclusion of my talk, I will say that it is possible to produce with cost-effective and is usually scalable devices on flexible substrates. We can also use them as tactile sensing, so autonomous sensors of movement, of presence, of mechanical presence. We can imagine in the future some smart electronics with piezo energy harvester, a power management, storing energy in a storage unit, and we can also imagine that this power management can include some single nanowire or multi-nanowire FETs in order to use some very low consumption devices in the power management system too. So this is the end of my talk. I thank all the members and former members of my team. I thank also the funding received from Europe, from France, and from the Region Centre. All this work was done at CERTEM collaborative platform. And ENSO European project has just finished, and we were involved in this project in order to help to build some interesting bricks for the autonomous microenergy sources. And you can have more information on this project on this ENSO website. Thank you very much. And if you have some questions, maybe I will stop to share my screen.
Yeah, thank you, ma'am, for such a nice presentation and informative talk. Now, I invite some of the questions. If you have any question, you can raise hand or you can put your questions in chat box. Hello. So when Sarvani has raised her hand, I'm unmuting her, and you can ask your question. Sarvani, you can ask your question.
Thank you, ma'am, for this wonderful talk. I have few questions. First one is to reduce defect in zinc oxide nanowire, we can anneal the nanowire. But I have found in some literatures that by annealing, the N-type nature of the nanowires slightly moves towards a p-type nature. So you have told that n-type nature is good for your device. So what do you say about this?
So if I understood well, you say that it can lead to p-type doping.
Yes.
This is.
Yes.
I would say it depends on the conditions of annealing. It depends on the atmosphere where the nanowires are annealed. What we did on our side is annealing in air or annealing in oxygen. And what we observed is it was decreasing the doping level, but it was still N-type doping. So I think it depends a lot of the duration and atmosphere of annealing, and p-type doping of zinc oxide nanowires. It's a very strong thing. It's not easy to do. It's not very stable. So we didn't want to do p-type doping. We just wanted to decrease the n-type doping, and with annealing in air and annealing in oxygen, it's possible. I hope I answered to your question.
I have one more question. That have you ever tried to fabricate this device on a patterned zinc oxide nanowire?
On a patterned side layer. We tried with on areas with very small diameter with zinc oxide layer on these surfaces. And in fact, no, what we did is we patterned the gold bottom electrode, and we tried to make the growth. And what we saw is that we had on the gold areas very dense and nanowires touching themselves, and with a much higher density than on a full gold layer, even with the same synthesis conditions. So it's not so easy to make to control the place where the zinc oxide nanowires will grow. So we can do it, but not at the level of 1 nanowire.
And regarding the metallization process after fabrication, when you are forming the top contact electrode, how can you ensure that that contact electrode is not touching the nanowire? As you wanted to fabricate that electrode over the insulating layer, is it right?
You mean, are we sure that the contact is good and that there is no short circuit, maybe?
Yes.
So we control all our final devices are controlled in terms of impedance, electrical impedance, and the measurement of impedance gives us a good way to check if there are some short circuits. With parilency deposition, the coverage of the nanowires is very conformal, very high quality coverage. So usually we don't have short circuit problem. We had some problems previously when we did some spin coating of PDMS or PMMA, but with parilen it works quite well.
Thank you so much.
You're welcome.
So I thank Professor Gailen for such a nice presentation and sharing her research work with all of us. We enjoyed it a lot. Thank you, Professor.
Thank you, and have a nice conference.
Thank you, Gulin, and hope in future you will also accept our invitation and sometime visit India after the COVID-19 is going to normal. Thank you very much, and how we can work together for the betterment of the society. Thanks our organizing committee. Thank you, madam. Namaskar.
Goodbye. Thank you. I hope we will have other opportunities soon. Goodbye.
Yes. Thank you.
our next speaker is Dr. Sonia Mukherjee. I welcome Dr. Mukherjee. She is DST inspired faculty in Department of Colloid and Material Chemistry, CSIR, IMMT Bhubaneswar. So I welcome Dr. Mukherjee and I invite her to present her research work with all the participants here at AFM 2020. Dr. Mukherjee, can you hear me?
Am I audible?
Yeah, you are audible. Yeah.
Yeah, my slides are visible or?
No, your slides are not visible. Please share your slides.
Okay,
Share
just a
screen.
minute.
Yeah,
Uh,
share screen. In the downward panel, there is share screen. You open your slides in another window.
in the downward.
Green symbol is there. Share screen.
Yeah, share screen. Yeah, I
Yes.
think I have shared
Yes.
it.
Yeah, you have shared slideshow, please.
Yeah,
Go to slideshow.
just a minute.
Full screen. Yes, now it is full screen.
Just a minute.
Okay.
Share.
Yeah. Is it visible?
Yes. Yeah,
Thank
now
you
it
very
is
much.
visible.
Yeah. Thank you. So, good afternoon, everyone. Myself, Dr. Somdatta Mukherjee, and I am an INSPIRE faculty at CSIR IMMT Bhubaneswar. The topic of my today's talk is multiferroic gallium ferrite nanostructure for ferroelectric memory applications. I hope everybody can see me and hear me properly, right?
Yeah. That's nice.
Thank you. Yeah, thank you. Okay. So this is the outline of my talk. I will begin with a brief introduction to multiferroics and possible technological applications, mostly the ferroelectric memory applications. Then I will come to the main system, that is gallium ferrite. Why I have chosen particular this system for our study, and then I will go to I will discuss gallium ferrite thin film ferroelectricity based on its the conventional orthorhombic polar PC2N structure. And finally, I will discuss another part of the same system, gallium ferrite nanocrystal, but with a novel polar R3C phase, which we hope that this system with this polar novel R3C symmetry will show better ferroelectricity than its conventional PC2N phase. So coming to this basics of multiferroism, I think it's quite known that multiferroics are the systems which are the systems in a single phase, two or more basic ferroic properties coexist. That means basic ferroic properties means ferroelectricity, ferromagnetism, ferroelasticity. Ferroelectricity is orientation of polar dipole moments that can be switched by application of external electric field. Similarly, magnetization that can be switched by external switching of external magnetic field, that is called ferromagnetism. Similarly, the ferroelasticity. And if the two or more ferroic properties coexist in the same phase, then those systems are called multiferroics. But the interesting feature is that not only these two or more ferroic properties coexist, the order parameters also can be coupled to each other. And for example, in a ferroelectric ferromagnetic system, this polarization and magnetization, they can be coupled to each other, so that we can access the polarization switching by application of external magnetic field and vice versa. So from basic physics point of view, these systems show very novel properties based on this magnetoelectric coupling. And coming to the technical application front, these systems are mostly studied aiming to the application in multiferroic memories. For example, this is a schematic of magnetoelectric random access memory, where the binary memory is stored in this blue bottom magnetic layer, and the magnetization of this layer can be switched by switching the electrical polarization of this adjacent ferroelectric antiferromagnetic layer using the exchange coupling, and in this way the magnetization can be switched by application of external electric field instead of external strong local magnetic field, which consumes more energy. Then this kind of memory will be more energy saving. And the second example is, this is a 4-state resistive memory, where a particular ferroelectric, ferromagnetic insulating few nanometer thick multiferroic layer is sandwiched between a magnetic electrode, and in other side there is a non-magnetic metallic electrode. And this this kind of memory uses the electroresistance and magnetoresistance tunneling property, so that the both electrical polarization up and down coupled with I should not say couple, that the combination of ferroelectric up and down polarization and magnetization, the both side polarization, that can be used. But in this case, the magnetoelectric coupling should be very low or weak, so that we can access that polarization up, magnetization up, polarization up, magnetization down, polarization down, magnetization up, and polarization down, magnetization down, these 4 states. And accordingly, these memories are called 4-state resistive memory. So in a given memory device, given size of memory device, since we can access 4 resistive memory states, the memory density will be data density will be very high in this class of system. So these are from technological application point of view. So these systems are very interesting. Either these multiferroic materials with a combination of ferroelectricity and any one kind of long-range magnetic ordering, that could be antiferromagnetic or ferromagnetic. Those with or without strong magnetoelectric coupling are very interesting from the point of view of non-volatile data storage application. Now, we know these multiferroic systems are very promising, but in actual point of view, there exist very few multiferroic systems that shows both the electrical polarization and long range magnetic ordering at room temperature. And at this point, gallium ferrite is a very interesting system. This is because this system shows ferromagnetic property, and the magnetic transition temperature can be tuned to above room temperature. The system crystallizes in orthorhombic polar PC2N symmetry. This is room temperature piezoelectric and pyroelectric. But if we look for the ferroelectricity or ferroelectric property of these systems, if we take single crystals or bulk polycrystalline systems, this system shows very high leakage current. And due to this very high leakage current, we cannot apply the sufficient electric field for switching the electrical polarization, and hence this system, this gallium ferrite, as polycrystalline bulk form or single crystalline form, is unable to show ferroelectric polarization switching. And here comes the epitaxial thin films of gallium ferrite, which are grown using pulse laser deposition on single crystalline substrates. If we apply electric field for polarization switching, these systems, these films may not show polarization switching. But if we look at the nano piezoelectric domains in the systems, as we can see in this picture, these nano piezoelectric domains shows phase which are completely out of phase. That is, we can see this high contrast in this phase plot of this PFM imaging, where these piezoelectric nano domains are 180-degree phase apart. And from this 180-degree phase apart, we can expect that this system should show ferroelectric switching. And in a more recent work in 2016, the Song et al., they have showed nearly saturated ferroelectric polarization saturation upon reversal of electric field. And they used a gallium ferrite epitaxial thin films deposited on a strontium ruthenate and strontium titanate substrate, using strontium ruthenate as the conducting bottom electrode and PT as the platinum as the top electrode. And here we see these systems, though shows high remanent polarization around 50 microcoulomb, the coercive field is very high compared to the available room temperature for electric systems available. And this coercive field is around 1400 kilovolt per centimeter. Then we can think that this system, if we use it in random access memory devices, will be very energy consuming. And the current density, when measured on this 200 nanometer thick films, the current density was quite low, around 10 to the power 6 ampere per centimeter square. So, and due to this low leakage current density, this system, this epitaxial thin films, was able to show this ferroelectric polarization switching. So these epitaxial films showed ferroelectric polarization switching and confirmed gallium ferrite as a room temperature ferroelectric. But epitaxial films, those have some drawbacks if we look from the application point of view. First, it uses the pulse laser deposition, which is a very costly deposition technique, and the uniformity of the film that comes within very small area, surface area, that comes in millimeter scale, about 10 mm, and it uses expensive single crystalline substrates like yttrium stabilized zirconia and strontium titanate. Again, the epitaxial films use costly conducting bottom electrodes, and it is a high temperatures, it uses very high temperature synthesis process around 800 degrees Celsius. So from these points, we see that this epitaxial thin film growth using pulse laser deposition, though they are of good quality ferroelectric films, but if we think about technical application, we need large scale production. From that point of view, these are not that much attractive. So from this point, we thought of synthesis of this gallium ferrite thin film using solution spin coating deposition on commercially available substrate like platinized silicon. Actually, we tried in both platinized silicon and commercially available N-type silicon substrates because these are easily available, and spin coating gives us thin film which are very large, which are very compatible for large scale production. So aiming those, we tried to deposit this gallium ferrite thin film on commercially available substrates. We chose this platinized silicon substrate because for electrical characterization, that for ferroelectric characterization, we need a conducting bottom electrode. So we chose this platinized silicon substrate, and here if we see this X-ray diffraction pattern of this film, we see that the family 010 this gallium ferrite peaks are available only in this X-ray diffraction pattern, and those peaks which are marked with star and the substrate peaks, if we remove them, then we can see only this 010 family peaks are present. Thus, this though these films are facile spin coated synthesized, these films also shows that oriented kind of film, and the orientation is along out of plane crystallographic B axis, which is the spontaneous polarization direction of this film. And this cross-sectional SEM image shows the thickness of the film is around 200 nanometer. And since we have used a bottom electrode that is platinum and that is polycrystalline in nature, our films are also polycrystalline in nature. But X-ray diffraction study reveals these films are or with orthorhombic PC2-1N symmetry. And this is the room temperature Raman spectra of the gallium ferrite film deposited on PTSI and silicon substrate. And from these peak positions, we see the for both the films, the peak positions are almost same. So we can say that the films are almost strain-free in nature. Now coming to the electrical properties, we try to study the electrical property of this film by depositing gold top electrode of 200.2 mm diameter on top of this gallium ferrite films. We can see this capacitor geometry of this gallium ferrite film, on which this AU top schematic of this AU top electrodes. And when we tried to measure the macroscopic polarization switching, we see this macroscopic polarization switching is not completely saturated in nature. And why these are not saturated, we try to measure the leakage current as a function of electric field, and we find that the electric field, we find that the current density, leakage current density, that comes around 3 into 10 to the power 5 ampere per centimeter square, which is an order of magnitude higher compared to that epitaxial gallium ferrite thin film that was deposited on SRO-STO. So we were unable to get saturated ferroelectric macroscopic hysteresis loop on this polycrystalline film. Then we thought, if in macroscopic scale we are not able to get, we thought to go for its microscopic scale, and we used piezo response force microscopy. We can see these two plots. This is butterfly amplitude plot, and this is the phase plot. And what we did, we used piezo response force microscopy, and we selected a particular nano piezo domain. And within the nano piezo domain, we switched the electric field from minus 40 volt to plus 40 volt. And we found that within a particular piezoelectric nano domain, the piezoelectric phase switches 180-degree phase, and this 180-degree phase switching is indicative of ferroelectric polarization switching. And within a single piezoelectric domain, the average coercive field based on the thickness of the film, we calculated around 700 kilovolt per centimeter, which is quite close to that we observed in case of epitaxial thin film of gallium ferrite. But if we want to make device, we cannot take piezoelectric nanodomains. So that's why what we tried, we did the piezoelectric microscopy. We selected a 2 micrometer cross 2 micrometer region on the film, and we poled this region using a 40 volt electric voltage. And at the center of this 2 cross 2 micrometer region, we selected another region of 1 cross 1 micrometer region, and we tried to pole this center region in opposite direction with a positive 40 volt voltage. And after that, what we did, we removed the polling part, and we just did a piezo response force microscopy on the region around where we did the polarization polling experiment. What we found that this high contrast region, but this dark region shows this negatively poled region, and at the center this bright region shows the positively poled region. So we were able to show the polarization switching upon polling the film from negative to positive field. So in this way, we have showed that our gallium ferrite polycrystalline film deposited on commercially available platinized silicon substrate using a facile spin coating synthesis technique that is also able to show room temperature ferroelectric polarization switching, which is very promising for ferroelectric memory devices. So up to now, what we find that this ferroelectric polarization switching in polycrystalline film, but if we see this coercive field for polarization switching, that is around 700 kilovolt per centimeter. That is also very high for if we think from application point of view. So we thought to go for the same system, we can, if we can probe the system by changing the shape and size of this system, so that we can probe the quantum effect in this same system. And so for that reason, we try to synthesize gallium ferrite nanocrystals. And for this purpose, we synthesized gallium ferrite nanocrystals using a hydrothermal route. And this hydrothermal route is a low temperature synthesis process. And using this hydrothermal route, we at 50 degrees Celsius synthesized gallium ferrite nanocrystals without any shape defining or capping agent. And we obtained a novel shape of these gallium ferrite crystals, which is truncated hexagonal bipyramidal shape. Also, when we studied with extra diffraction of these crystals, we found these crystals for the first time. We reported crystallized in novel P2121 symmetry. Now, this P2121 symmetry is novel for this system, but we were mostly interested to find the ferroelectric nature of gallium ferrite. And so we tried to see the phase evolution of this system, structural phase evolution of this system as a function of temperature. So what we did, we performed temperature dependent X-ray diffraction. And this is the temperature dependent X-ray diffraction as a function of temperature from room temperature to around 773 Kelvin. And you can see these a few peaks which are marked with these red arrows that gets disappeared with increasing temperature, and around 648 Kelvin, these peaks with red marks completely disappear. Therefore, we can assume the system with gallium ferrite with P2121 symmetry undergoes a structural phase transition at around 648 Kelvin. And this structural transition is also supported by our differential scanning calorimetry measurement, where we can see this endothermic peak at around 630 Kelvin. There is slight temperature difference between this temperature dependent X-ray diffraction and this scaling DSC. So with this increase, since these a few peaks gets disappeared with increasing temperature, we can assume that the system undergoes a structural phase transition going from lower symmetry to higher symmetry. Then we try to probe the newly found phase at 648 Kelvin using Rietveld refinement. And for this purpose, we tried to refine the X-ray diffraction patterns of the phase at 648 Kelvin using rhombohedral polar R3C phase, and as well as with the non-polar R3C symmetry. Though it is practically is not possible to differentiate between these two polar and non-polar phase, that is R3C and R3C, still we tried to fit with this Rietveld refinement. And what we found that a better goodness of fit using R3C phase. So from this, we propose that our system goes to a novel polar phase, which is R3C, and this system, this polar R3C phase is very promising to show ferroelectric nature in multiferrite system. Like we know about bismuth ferrite that crystallizes in polar R3C phase, and which is a very well-known room temperature ferroelectric. And this is the proposed crystal structure of polar R3C phase that is shown here. And this this 648 Kelvin phase, polar R3C phase, is also corroborated using the Raman spectrum. And here with this rhombohedral R3C polar phase is expected to show a total 13 Raman active modes. And here we identified 13 Raman active modes. And here this above 260 centimeter inverse, those are expected to show this oxygen-oxygen bonds, and below 160 centimeter inverse, these bonds are expected to show this gallium oxygen stretching and compressing bonds, and in between from 160 to 260 centimeter inverse. These bonds are, these peaks are corresponds to iron oxygen stretching and compressing bonds, vibrational modes. Coming to the microstructural analysis, this is the FEACM spectra plot of this gallium ferrite THBP nanocrystals in polar R3C phase, and we found a average axial size of these nanocrystals of 150 nanometer, and in this HRTM image we found the interplanar spacing that is around 0.27 nanometer. Now, when we did the Rietveld refinement, from the Rietveld refinement extracted data, we calculated several high indexed peaks, and these 0.27 nanometer interplanar spacing corresponds to high index 10 planes of R3C symmetry. Now, since this system undergoes a temperature-dependent structural phase transition, we also tried to probe the structural phase transition using the temperature-dependent dielectric analysis. And this is the temperature-dependent real part of dielectric constant as a function of temperature from within the range 300 Kelvin to almost 780 degree Kelvin with varied frequency from 0.1 kilohertz to 1 megahertz, sorry, 2 megahertz. And what we found that at all frequencies, the dielectric constant shows clear dielectric anomaly at around 650 Kelvin, which is very close to the structural phase transition temperature from P212 symmetry to rhombohedral polar R3C symmetry. The same dielectric anomaly is also visible in the imaginary part of dielectric constant. And from this plot, we can say the dielectric constant of this newly found R3C polar phase of gallium ferrite is around 7. Now, coming to the ferroelectric polarization analysis, since we know the well-known room temperature multiferroic bismuth ferrite that crystallizes in polar R3C symmetry, and when we found the polar R3C phase in our system, gallium ferrite, we were very much excited whether this system, gallium ferrite, also shows ferroelectric polarization switching. However, our system is nanocrystalline structure, and there is a irreversible phase transition which is just 200 Kelvin above. So that is why we are not able to sinter our gallium ferrite pellet. That is, we for this macroscopic polarization measurement, we prepared our sample as a hard pellet, but we were not able to sinter that pellet at high temperature. So that is why the macroscopic polarization measurement was a little difficult. And though we got this polarization plot at polarization as a function of electric field, and the polarization saturation is not very clear in this plot. So the ferroelectricity in this system is still under review. So we need to perform more studies whether this system shows ferroelectric polarization switching or not. And we also tried to perform study the nano piezoelectric domains, taking a particular nano crystal, and we obtained this amplitude butterfly loop and this polarization reversal measurement. However, from this measurement, it is not very clear whether the polarization reversal, even at nano domain, is very clear or not. So the ferroelectric nature of this system is still under study. So I will come to the summary of my talk. And we synthesized oriented polycrystalline gallium ferrite thin film using a very easy synthesis spin coating, and we obtained ferroelectric polarization switching, that is polling. We were able to poll the gallium ferrite thin film using a very high electric field, and the coercive field for polarization switching was very high, around 700 kilovolt per centimeter. That is the drawback for this system to be used in ferroelectric or multiferroic memories. And for this purpose, we try to probe this system as to synthesize in nanocrystal form. We used hydrothermal synthesis process to synthesize gallium ferrite nanocrystals, and we obtained unique truncated hexagonal bipyramidal shape with novel P2121 symmetry. And as when we studied this P2121 phase, the temperature evolution of the structure of this system, we found a structural phase transition from P2121 phase to polar R3C phase at around 648 Kelvin. This structural transition is also corroborated by our temperature dependent dielectric measurement, which shows dielectric anomaly at around 650 Kelvin. However, though we are very interested to see the ferroelectric nature of this R3C polar phase, still the polar R3C phase, the ferroelectric nature is under our study. Thank you.
Thank you, Dr. Mukherjee, for such a nice talk. Now the session is open for questions. If anyone has any question, he or she can raise hand, or they can type their questions in chat box. In the chat box, I could not find any question, and no one has raised a hand. So, okay, there is one question from Nilay Mohanty.
Sure.
Nilay, unmute yourself. Nilay, you can unmute yourself. If you are not able to unmute, you can type your question in chat box.
I think I have given such a nice presentation. Nobody is interested to.
But no one is there. No, so no one has any queries. No one has any question. Okay, that's very nice. So I thank the speaker for for presenting her scientific findings, sharing the scientific work with us. Thank you, Dr. Mukherjee.
Thank you. Thank you very much.
So now our next speaker is Dr. Alluri N.M. Rao. Dr. Rao has received his PhD from Jeju National University, South Korea in 2018. Presently, he is postdoctoral researcher at Nanomaterials System Lab, Jeju National University. He has filed 6 patents and he has 48 publications in international journals. Some of his work has faced places as journal cover page design in Journal of Material Chemistry C, small and nanoscale. He has co-edited 2 books and he has written 2 book chapters also. He is member of American Physical Society. So today, Dr. Rao is presenting his talk on flexible, multifunctional piezoelectric materials for nanogenerators and self-powered sensor. So I welcome Dr. Rao to present his talk.
Thank you, ma'am. Thank you for a nice introduction. I'm going to share my slides.
Yeah, sure.
Just a minute. Is it visible, ma'am?
Yes, it's visible.
Oh,
yeah.
Yes.
Yeah, you're audible too. Yes.
Thank you to the chair for giving this opportunity to present my work. This presentation is a little extension of my workshop presentation happened on 26th. Following that, I'm going to present flexible and multifunctional piezoelectric materials for nanogenerators and self-powered sensors. Coming to my talk contents, my talk contents mainly involved in the 3 parameters. One is development of nanomaterials and the development of energy harvesters to harness the mechanical energy, and followed by that development of self-powered sensors. Here, these are the left-hand side showing that these are the contents: motivation for harnessing mechanical energy, growth of piezoelectric structures, and multiple piezoelectric nanogenerators, and as well as corresponding self-powered sensors or the systems. And following that, summary. Here, if you see that, what is the motivation behind to develop these this kind of flexible piezoelectric nanogenerators means, if you see over the last few decades, we are developing electricity by using the traditional energy sources. But the use of traditional energy technologies requires a huge amount of natural resources, such as coal and fossil fuels, as well as natural gas and a few other parameters. The consumption of these natural sources electricity, but at the same time, there is a lot of byproducts are existing, though such are nothing but greenhouse gases. These greenhouse gases are highly harmful to the society and as well as to the nature. Because of this, we are going to face a lot of issues in future. So in order to solve these parameters, and at the same time, we need to make our electricity demand and supply. For that point of view, many researchers across the globe, people are concentrating on clean energy technologies. These clean energy technologies mainly depend upon the clean energy sources, such as solar source, and as well as wind source, and geothermal, and hydrogen, and water energy, and bioenergy. And somewhat people are using nuclear energy very effectively also. And other than these, there is another useful clean source is mechanical energy. So by using all these energies, in recent days, many of the researchers, they developed a very useful clean energy technologies which can provide green energy. There is no harmful to the nature and as well as to the people surrounding to the plants or anything. So if you see here, among these all clean energy sources, mechanical energy is not explored full potentially. So from Professor Jadal Wang, he introduced 2006 piezoelectric nanogenerator as a prototype to harness the mechanical energy. From that onwards, many researchers across the globe, people are developed various types of piezoelectric nanogenerators. Before our presentation, Professor Gailin also explained about piezoelectric generators using the zinc oxide nanogenerators, but the output power is maximum developed around 35 microwatt from the Professor Gailin group. But still, many other groups, they developed a huge amount of power, but still it is questionable whether it is possible to make a commercialization or not. Here, if you see right hand side bottom image, we have lots of waste mechanical energy in the society, but still we are unable to use. Here we are going to propose a few few energy harvesters such as piezoelectric or triboelectric energy harvesters. By using this, we can develop standalone micro power sources as well as self-powered sensors. Here, these standalone micro power sources is useful to drive any kind of low power consumed electronics as well as wireless sensor nodes and implantable devices. Or the devices itself, it can work as a bio or chemical sensors and optical sensors and a few other possible sensors in various fields. Here, I will give you one simple example. How much energy we are wasting in every day in our life means. If you see here, South Korea, in South Korea, the on-road vehicles on per day is almost like a 22,000 vehicles moving on the roads. At the same time, all these vehicles are covering around 3 lakh kilometers. If you see such a small country, they are producing this much amount of huge vehicles, using huge number of vehicles, and they're going this much kilometers. If you see from our India is almost like a 20 times higher than the South Korea. So the on-road vehicles capacity on Indian roads is very, very high. So at the same time, the development of mechanical energy is also very high. If you are able to develop highly potential piezoelectric nanogenerator, we can successfully utilize these nanogenerators to harness this all waste mechanical energy in useful way. Following to that, we are working from over the last 6 years on these piezoelectric nanogenerators, and we are facing few challenging parameters. Till now, we reached by using various piezoelectric structures and nanogenerators until 100 milliwatt per meter square. And still, many people are looking to develop or looking to improve this power until 1 watt or 2 watt or 3 watt by changing the various structures. If you see this left-hand side image is portraying the overview of the piezoelectric materials. As we know that during my workshop talk I gave, we have various various classifications of piezoelectric materials, such as inorganic piezoelectric materials, organic piezoelectric materials, and composite piezoelectric structures. If you see each and every category, we have different kind of advantages as well as different kind of disadvantages. If you see inorganic piezoelectric nanomaterials, high D33 is available, and at the same time, a high electromechanical coefficient is also available, and it will give you the better performance. But it is suffering with toxicity and as well as a brittleness and internal leakage current, and it cannot accept high mechanical force because of this brittleness. So on the other hand, the organic polymers also have advantages and disadvantages. If you see organic polymers such as PVDF and its copolymers, or otherwise the collagen and few other polymers, have a good flexibility in nature, and as well as it will accept a high force. And the synthesis procedure is cost effective, and as well as polling free analysis is also possible, like a self-polling analysis of PVDF. And the processing time is also very, very low, but it has a low D33, low piezoelectric coefficient, and low dielectric, low relative permittivity. So all these drawbacks are restricting the use of these applications. So recently, Professor Kezeli, he was introduced in piezoelectric nanogenerators, composite piezoelectric nanogenerators, by the proper selection of these two categories and mixing into making a composite structures to solve all these kind of individual drawbacks, such as brittleness and as well as accepting the force, all these parameters. But still, these composite structures also have some kind of disadvantages. The disadvantage is choosing the right materials and making the proper perfect weight ratio combinations to deliver the high amount of electricity, to generate the high amount of electricity. And in order to do this kind of analysis, it requires a lot of processing time and a lot of efforts we need to make proper designing of the composite materials. So till now, people are developed this 100 milliwatt per meter square output. Still, we are going to look on to improve this output by modulating these parameters, such as selection of materials and suitable polymer and weight ratio, and tailoring the device design and load matching analysis. By designing piezoelectric composites with suitable piezoelectric coefficients, we can able to generate the high power density of piezoelectric generators. If you see from our lab, we developed over these years from our lab, we developed many of the nanogenerators. Just a minute. Many of the nanogenerators. Here, our NMSL group mainly working on energy conversion and storage analysis. From our energy conversion group point of view, we developed a few prototypes and as well as a few different types of nanogenerators. If you see here, we mainly concentrated on piezoelectric materials and ferroelectrics and as well as semiconductors and one-dimensional and two-dimensional and three-dimensional materials such as TMDs and dielectrics and polymers. If you see here, the piezoelectric and ferroelectric materials point of view, we are able to develop microparticles and as well as nanoparticles and nanocubes and nanorods. And according to the synthesis techniques, we developed various kind of individual nanomaterials. And at the same time, by using these nanomaterials with a suitable polymer supporting template, we developed various kind of composite structures such as a hemispherical strip and spherical beads and linear worms and wavy pattern worms and planar films and micropillar structures and as well as the rough film. According to this, we analyzed how much output power we can able to generate by using these kind of structures, and we systematically investigated the energy performance, and we developed in various, we published in various respective journals all these kind of works. But in the present topic, I'm going to discuss only these piezoelectric nanogenerators, and I'm not going to touch these piezotronic and piezophotonic and as well as the triboelectric nanogenerators. So if you see, by using these piezoelectric structures, just a minute. Piezoelectric structures. This slide I already discussed in the workshop presentations, and still I will give you a little more information. And by using these piezoelectric structures, we are able to develop four different types of piezoelectric nanogenerators. One is zinc oxide pure nanogenerator, and as well as polymer nanogenerators and composite nanogenerators. And recently we developed perovskite ceramic, pure perovskite ceramic flexible nanogenerator by the growth of barium titanate on a single wire, single flexible titanium wire. And if you see here, this bottom images are showing the different kind of device designs and its performance we investigated. And these are all these works are published in this respective journals. And this right hand side image is showing that the generated energy is successfully utilized to power up these kind of LEDs and as well as sign letters. And this center image shows that these different four types of nanogenerators lies in these three categories, such as planar type as well as single wire and fiber and strip type nanogenerators, and as well as this wavy pattern nanogenerators. Coming to the discussions of piezoelectric structures. Today I'm going to explain only these two materials. One is antimony sulfur-iodide, and next one is the bismuth titanate based piezoelectric nanogenerators as well as the self-powered sensors. Coming to the first antimony sulfur-iodide point of view, we developed as SBSI microwires by using the solid state conventional solid state reaction technique by following the additive of pure elements 1:1. This iodine 1:1 ratio I used, and as well as 2 ratio we will use. It's depend upon the proper amounts we are able to develop for this SBSI wire. Here, if you see here, we used in this here we used two different kind of temperature conditions, such as 250 degrees as well as under 350 degrees. In 250 degrees point of view, we observed a pure single crystalline phase and without any additive impurities, and the resultant XRD pattern is perfectly matched with the space group PNMA and ISD number. And here, if you see here, the major intensity peak 310 and as well as 330 and 200. These are the higher intensity peaks, and which is perfectly matching with the orthorhombic phase structure. And if you see this left hand side image, schematic diagram shows that the atoms oriented in 001 plane and as well as 010 plane, showing that it has some kind of a ribble like structure. And the grown SBSI microwires are grown SBSI microwires having a size of 1 to 2 micrometer in diameter, and as well as the length is around 20 to 50 micrometer. Here at the same time, we changed this temperature from 250 degrees to 350 degrees, but we experienced a little impurities in the XRD pattern, but I didn't show here, but it was there in the paper. We experienced some little kind of impurities that is due to this decomposition of iodine. Iodine will not sustain at 350 degrees centigrade. So the optimum temperature to prepare this SBSI microwire is around 250 degrees. So coming to this bismuth titanate nanoparticles point of view, we followed the sol gel technique, the conventional sol gel technique. In this conventional sol gel technique mainly involves hydrolysis and condensation and decomposition reactions. By following these three reactions, so we are successfully developed the bismuth titanate nanoparticles, and these particles are obtained at 600 degrees centigrade 1 hour processing temperature in the tubular furnace. And the corresponding XRD pattern, the major intensity peak at 30 degrees peak 117 plane clearly indicates that the nanoparticles are in orthorhombic phase, and the elemental mapping analysis confirms that existence of bismuth and titanium and oxygen elements. And further, by using these particles, we developed the nanogenerator and as well as the breath sensor, and these two we separately investigated, and this NTC thermistor we are separately investigated. And in this talk, I am not able to discuss about this NTC thermistor, and I am only going to discuss in nanogenerator and breath sensor. So if you see SBSI piezoelectric energy harvester, here generally SBSI piezoelectric energy harvester, individual particles are highly brittle in nature. So we use the PMM as a supporting polymer template. In this polymer template at particular weight ratio, we mixed the SBSI microwires, and we prepared the composite film by using the solution casting technique, and later it was sandwiched between the two aluminum electrodes and followed by that anti-static layer we used to control the external noises such as electric noise as well as humidity and the temperature environments. And further we packaged it with the completely packed with the PDMS layer. If you see here, this left hand side bottom B and C images informations gives the voltage and current analysis at particular 2 newtons force, and the D graph explains that the load resistance analysis of this SBSI PMMA PNG device, and it is almost delivers that 5.5 microwatt per meter square output. And this E figure demonstrates that the generated amount of energy we are able to utilize to drive this 3 commercial green LEDs. And if you see, coming to the next point, here this SBSI have a multifunctional properties. One is a piezoelectric property, and as well as it has a good optical properties. If you see here, this right hand side image, by using this SBSI microwires, we developed a photo detector, and the A image shows that dark current, whenever we are applying a certain kind of bias voltage, the dark current is very, very minimum. And whenever it was exposed to the 630 nanometers wavelength source with the different intensities, the current is raised linearly. This is clearly indicates that the SBSI microwires are highly sensitive with this wavelength source. And B image shows that the time dependent analysis of this SBSI wires with respect to the various light intensities. Here if you see 1.94 milliwatt per centimeter square to 17.946 milliwatt per 17.46 milliwatt per centimeter square, we varied systematically, and the corresponding photocurrent is also varied systematically. And further we calculated the rise time and the decay time by using this starting intensity of wavelength. Here if you see, the rise time is almost lies around 0.1 seconds, and the decay time is around 0.01 seconds. This is somewhat comparable with the zinc oxides photo detector response. And further we investigated the piezo piezoelectric output with respect to the light. Here if you see, D images is the optical images during off condition and as well as the on conditions. Here if you see, this box line is indicates that we placed the SBSI PMMA photodetector vertically to the rotary setup. In this rotary setup, when there is a this rotary wheel is acting on the device, there is a piezoelectric output voltage. This piezoelectric output voltage is fully controlled with the light sources. If you see here, D figure, right hand side, when there is a light is exposed on the device, the output potential is systematically reduced. It's clearly saying that the SPSI wire, the SBSI PMMA piezoelectric nanogenerators output is systematically reducing with respect to the change in the intensity of light intensity of 630 nanometers wave source. Here it is, the reduction in the output voltage clearly indicates that increase in the conductivity, and we tested a similar way second device. The second device also gives a similar kind of output. It clearly says that the SBSI PMMA based photodetector has a good repeatability and as well as good change in output with respect to the light intensity. They are by using this one, we developed a self-powered photodetector. And coming to the next second section of this presentation, bismuth titanate PVDF based piezoelectric nanogenerator. Here the novelty of this work is mainly ion typed piezoelectric nanogenerator. Till now, we have shown that planar type piezoelectric nanogenerator. Even previously, Professor Gailin is also explained planar type piezoelectric nanogenerator. This kind of planar type of nanogenerators is not useful in all kind of applications. So if you want to monitor some nonlinear surface motions, we need to develop according to the substrate. According to the object type. So in such cases, this kind of yarn type piezoelectric nanogenerators are highly useful, because this yarn is highly flexible and as well as highly twistable also. So here we are developed this yarn type piezoelectric nanogenerator by using a layer by layer brush coating technique. Here if you see, I already explained that the bismuth titanate nanoparticles were prepared by using the sol gel technique, and this Raman spectra also clearly indicates the orthorhombic structure, and this 848 peak majorly indicates the symmetric stretching of titanium and oxide bonding, titanium and oxide bond. And further, these all Raman active modes also indicates that oxygen, titanium, and oxygen symmetric and as well as asymmetric stretching. And here, if you see, XPS pattern is clearly confirms that the existence of bismuth and as well as titanium and oxide, all the elements. And this right hand side image clearly shows that the ferroelectric analysis of this bismuth titanate, and it has a polarization saturation is almost like a 6 to 8 microcoulomb per centimeter square. Here the top image is clearly indicates the elemental analysis. After that, we in this slide, we are able to show you layer by layer brush coating technique. This brush coating technique recently we received the Korean patent also. And if you see here, this is very, very simple technique, and moreover, it's a cost effective, and it is not harmful to the developer. Initially, we have taken the flexible yarn and we washed with the acetone and ethanol. Later, we made it dry. And after that, the AZ electrodes we deposited by using the manual layer by layer approach. And 2 times here we deposited the AZ material, and followed that further we prepared the slurry with the bismuth titanate and as well as a pyrrolidine solvent. With that solvent we coated the material, and followed by that we used here PVDF layer. Here why we used PVDF layer, in the sense of PVDF layer, it will act as 2 ways. One is it will control the brittleness of this bismuth titanate nanoparticles, and next it will it will avoid the short circuit between this top AZ layer and as well as this bottom AZ layer. So this PVDF it can act as a dual role. And further top electrode, we use the same AZ material, and followed by that we dipped the whole device into the PDMS solution. And here this central image is showing that inset image is showing the optical images of the device and its flexibility conditions. This left hand side right image clearly showing the cross-sectional images of the this yarn type of piezoelectric nanogenerator. Here B image shows that inclusion of bismuth titanate and as well as the PVDF for both materials, cross-sectional image. And the C image shows that without BITO nanoparticles, only with the PVDF. Here both here we are successfully able to distinguish by the elemental and EDS spectra mapping. Here if you see here the bismuth and titanium and oxygen layer we are explicitly identified by using the EDS mapping analysis. And this is silicon and carbon and oxygen. These three will comes from the PDMS packaging things. And this fluorine and carbon and as well as oxygen, all these things will come from the PVDS layer. In PVDF, there is a hydrogen element also, but this hydrogen element we cannot observe by using the EDS analysis. And platinum is the supporting material for measuring the FESM. So all this EDS element is clearly confirming that the yarn type piezoelectric nanogenerator is in good condition and systematic good condition. And good condition means layer by layer approach. And further we analyzed the energy harvesting capability of the yarn type piezoelectric nanogenerator. If you see here, before polling, the output of the yarn type piezoelectric nanogenerator is around peak to peak 20 volts to 10 volts range. After polling at 7 kilovolts for 12 hours, the output is increased systematically. And this left-hand side bottom is clearly showing the switching polarity of the device. In forward connection, when there is a mechanical load on the device, there is a positive peak generation. And in reverse connection, the peak is exactly opposite. It's clearly confirming that there is a clear phase shift between the signals, and it's confirming that the output is coming from the device, not from any other external sources. Later, we performed the force dependent analysis as well as the repeatability test of this flexible yarn taped PNG device. If you see here, we changed various forces. So from 1 Newton to 2 Newton, the change in output voltage is not so high, and it is providing the stable output. But whereas in the case of current, there is a slight change. This slight change may be due to the factors of PVDF and as well as this bismuth titanate interaction. This is due to the some kind of, we can say, some kind of little existing cracks. But if you see here, later we designed around 9 devices. In these 9 devices outputs, we observed almost similar kind of output. The deviation between the outputs is very, very less. And it's clearly saying that the flexible yarn-type piezoelectric nanogenerator is highly stable and as well as suitable for commercial applications. And later we demonstrated that without the force, there is no electrical output, and the corresponding LCD display is in off conditions. When there is a mechanical force acting on the device, there is a electricity generation. That electricity is able to drive this LCD display. And here, this right-hand side bottom image is clearly showing that the 5 green LEDs with low intensity, we are able to glow. And after that, here the output power is very, very low in case of antimony sulfide and as well as bismuth titanate PVDF layer by layer N-type device. Further, we used barium titanate and PDMS planar composite film. By using the solution casting technique, we developed the flexible film, and as well as this film has a highly rollable in nature. And the corresponding output power is many folds higher than the bismuth titanate and SBSI microwire. If you see here, the barium titanate nanocubes at 15 weight percentage in the PDMS polymer is generated a high amount of peak-to-peak voltage and as well as the short circuit current. And whereas in the case of a PDMS, pure PDMS nanogenerator doesn't have any output because PDMS doesn't have any piezoelectricity. generating output is only purely from BTO nanocubes. And if you see here, bottom right hand side image clearly shows the load resistance analysis of the device, and the generated output power is almost like nearer to the 7 milliwatt per centimeter square output, meter square output. And so till now we discussed about the synthesis of the piezoelectric materials of SBSI and as well as bismuth titanate and barium titanate and its corresponding energy harvesting capability. Now we are going to utilize this generated energy for sensor applications point of view. Here if you see why we are going for sensor applications means I already explained this slide in workshop presentation. Here the conventional batteries have many drawbacks. Because of these drawbacks, the battery based sensors are not able to use in wearable applications and as well as the stretchable applications. The drawbacks are large package in size and power consumption and high cost and limited lifetime and the risk of environmental pollutions. To overcome all these things, people are started to develop cell power technology. This cell power technology has a huge impact in future on various fields such as smart textile electronics and security surveillance and health monitoring applications. Here if you see this cell powered system concept, we can show in two ways. One is case one is utilizing the storage components, and case two is without utilizing any kind of components, directly generated converted mechanical energy to electrical energy to the corresponding user required applications. This case two is highly effective, but it requires a lot of investigations to control the generated amount of power and as well as the limits of user required electronics. User required electronics in the sense, suppose if you see a smartwatch requires less than 2 volts, but whereas in the case of mobile phone requires around 5 to 12 volts or 5 to 9 volts in that range. So we need, according to that, we have to develop our flexible energy harvesters in case to case. But whereas in the case of case one, by using the storage component, whatever the capacity of the input electricity, this energy will always controlled by using this storage component and corresponding electronic circuit. So in case one, we no need to think about the type of energy harvesters, but in case two we need to concentrate about our energy harvesting performance and the type of energy harvesters. By following this case one and case two categories, we developed a few sensors. Here we published many of the cell-powered sensors recently, like a Flexion sensor and as well as a cell-powered photodetector and intruder sensor, air pressure sensor, and as well as a fluid velocity sensor and a muzzle monitoring sensors. All these sensors have few advantages are abolishes the use of complex battery source and reducing the circuit components and pollution free, and it has a long life. And we are successfully utilizing the abundant waste mechanical energy. So if you see here, this right hand side image, here I am demonstrating the planar type fluid velocity sensor. Here this planar type device is almost like a 2 by 3 centimeter area. 2 by 3 centimeter area. Here that top images shows that voltage and current responses with respect to the water velocity 31.43 meter per second to 125.7 meter per second. Here this piezoelectric nanogenerator we expose it to the water tap. According to the Fouquet rotations, the amount of the water is falling on the device is varied. According to this, we are able to generate different kind of electric signals. So with this voltage and current outputs, we formulated the graph. Here if you see water wave, whenever we are increasing the water wave velocity, the output power peak is changing. Here this output power peak we are displayed in two conditions. One is water on conditions and water off conditions. Here if you see water off conditions, we are able to observe the little high voltage as compared to the water on conditions. Maybe here the relaxation of the electric dipoles is much more effective as compared to the water acting conditions. Here disadvantage of this planar type nanogenerator is not suitable to monitor all kind of applications such as nonlinear surface motions. For that point of view, if you see here, the practical limitations of planar PNG technology have 4 drawbacks, such as adaptability and flexibility in shape, and nonlinear surface motions, and poor performance. Here, if you see here, this right hand side image shows that one sports person has in different bending conditions, and at that time we need to know what is his health conditions, and if he had a typical bendings, is there any damage to the person or not. So in that cases, our piezoelectric nanogenerators also should be in highly flexible and as well as the stretchable. In these cases, the use of planar technology is restricted. So and in few other cases, whenever we use pure polymers, the performance is very poor. In that cases also, the planar type of PNGCs is not sufficiently useful. So by considering all these factors, we able to develop this yarn type piezoelectric nanogenerator. I already discussed with you the discussed previously the fabrication details and everything. Here we are able to show simple demonstration. If you see here, the as fabricated flexible yarn type piezoelectric nanogenerators is placed on the breathing mask at particular location, and further we packed well in the sense with the PDMS we covered systematically, and we monitored by using the our nanogenerator setup. If you see here B image, the B image clearly explains that there is a clear change in the output voltage when there is a inhale and exhale of human. Here, if you see, 5 different test subjects have 5 different kind of peak patterns. Each peak pattern has its own significance according to their health conditions. And further, we tested with slow breath condition and fast breath conditions. In both cases, we are able to clearly distinguish, because during fast breath conditions, the frequency of inhale and exhale is very high as compared to the slow breath, and corresponding the output is also changes significantly. And further, we observed the stability of the inhale and exhale of the device around 45 seconds is clearly showing that similar kind of peak patterns with a small change in the magnitude of the output voltage. This may be due to the inhale and exhale capacity of the person. And further, this inhale and exhale conditions, we are able to charge the commercial supercapacitor, commercial capacitor around 27 millivolts, 250 millivolts, using the 0.1 microfarad capacitors. All this information clearly demonstrating that the yarn type of piezoelectric nanogenerator highly useful for self-powered breath sensors. And this is the one simple example. We can successfully remove the complex battery source in this kind of applications, and this is highly portable, and wherever we can need and we can carry along with us. And but this has a small disadvantage. The disadvantage is the yarn type piezoelectric nanogenerator is a little longer in length. That is the one disadvantage, and the diameter is almost like a few hundreds of micrometer. So still this needs to be controlled in further applications. And for this, in order to overcome this, we developed adaptable piezoelectric hemispherical composite strip. This work also published in Nanoscale journal, and as well as we received the Korean patent for this prototype. Here, if you see this left hand side image, clearly shows the fabrication of this hemispherical strip by using the groove technique. Here, groove technique is very simple. Here, if you see, initially we have to choose some kind of a plastic PET substrate. By using some kind of rough metal needle, we can make the groove systematically, or otherwise simply we can use laser cutting also we can use. So by using this, by making this groove, we can design our size of the hemispherical, and this is all depend upon the user requirement. And if you see further, we attached some flexible titanium microwire, flexible titanium wire placed exactly center of this groove by using the rigid supports. And further, we poured the as prepared composite solution into the groove and heat treated at 70 degrees centigrade for 30 minutes. And later we peeled off from the PET groove. And if you see here, this optical image is clearly showing the hemispherical strip of the composite structure, and this corresponding FASEM clearly distinguishable of titanium wire and as well as the composite layer. And the center image shows the ferroelectric analysis of this BCNT nanoparticles, and clearly saying that it has a good considerable saturation. And this right hand side image clearly depicts the development of adaptable hemispherical strip piezoelectric nanogenerator. Here, as prepared hemispherical strips we transferred onto the flexible adhesive bandage by using a brush coating technique. We coated the top AZ electrode, and inner electrode point of view, the conductive TI wire will itself act as a substrate and as well as the inner electrode. And further we packed with the flexible PDMS polymer. And if you see here, this the inserts of the image clearly shows that the hemispherical strip we can fabricate in various lengths in sizes, and as well as it has a good twisting capacity and full twisting capacity, both capacities we have. And it's clearly saying that the as prepared flexible hemispherical strips are highly flexible and as well as twistable. And these kind of strips are highly useful to monitor the nonlinear surface motions. Here, if you see the energy harvesting capacity, biomechanical energy harvesting capacity is shown under two conditions: applying bending forces and as well as applying perpendicular finger forces. This left hand side image is showing the flexion and extension of our human fingers. So during that time, the device, hemispherical strip device, generates almost like a plus or minus peak to peak voltage is around 1.5 volts. And whereas in the case of perpendicular finger force, the hemispherical strip generates a little higher than the bending forces. And later we tested with the series connection of a few devices, and the correspondingly the output is also improved. And it's clearly saying that the hemispherical strip is highly suitable to generate a considerable amount of electricity. And later we developed a self-powered muzzle monitoring system. Here, if you see here, many of the works were published recently to monitor the human body motions, but all the works are based on planar PNG technology. So here we are able to show this hemispherical strip-based PNG technology. This kind of PNGs are useful to place any kind of locations on the human body. Here we are able to show certain parts such as elbow and hand fingers, and as well as the knee, and as well as foot pressure, and as well as the neck, and as well as this jaw movements. All these things are clearly saying that the device, as fabricated device, is highly suitable to monitor any kind of nonlinear motions, and the corresponding peak signals, voltage signals, is clearly distinguishable in each and every category. So this is clearly says that this kind of hemispherical strips is highly advantageous than the planar PNG technology. This work was published as a front cover in nanoscale, and extension of this work, still we are doing this smart suit and as well as hand glove designing. This here, previous slide I shown as prepared devices we place on the hand gloves and we monitor. But in future, we want to develop the glove itself is a piezoelectric nanogenerator. That is our aim, to monitor the whole human hand. So we are expecting soon we can able to design such kind of piezoelectric devices. So finally, coming to the conclusion, in this presentation, I'm able to show a few kind of piezoelectric nanostructures designed to harness the waste mechanical energy, and as well as a few prototypes to show beyond the planar PNG types. And skin adaptable micro piezoelectric strips are highly useful to monitor the whole human body motions. These are the things. And I must acknowledge my professors S.J. Kim, and as well as my Piezoelectric nanogenerators team members, and funding from the National Research Foundation of Korea, and facility support from the Research Instrument Center JNU. Thank you for your kind attention. If you have any queries, please.
Thank you, Dr. Rao, for such an illustrative talk. Now the session is open for questions. If anyone has question, he or she can type or raise hand. So here is one question in chat box. Dr. Rao,
Please tell me, ma'am.
why did you use PMMA as matrix for SBSL in the NG and not PVDF, considering that PVDF is a piezoelectric polymer and PMMA is not?
Yes. Actually, we have tested not only PMMA, we have tested PDMS and as well as PVDF and a few other polymers also. But the successful homogeneous mixing is happen in PMMA only. And SBSI and a few TMD materials are not suitable to disperse in the PVDF and as well as the PDMS. Even if you try to mix in this kind of polymers, the solidification of the material is not so good, and it has some kind of what we can say, the solidification in the sense, if you touch the composite film, you can feel some kind of moisture existing on the surface. It clearly indicates that the SBSI material is not properly reacted with the suitable solvent. That is the problem. Because of that problem, we have chosen this PMMA. That information we have clearly discussed in the manuscript, nanoenergy manuscript. I think I explained conventional.
Yes.
I think
yeah.
I'm facing some trouble. I'm unable to see the screen. Yeah, now I can.
Yes. Yeah. So now there is no other question, I think.
Okay. Thank you, ma'am.
So I thank Dr. Rao for his nice presentation, and
yes, ma'am. Thank you.
So there is one question. I think there is one question from Professor Goylan. Is it possible to? Yeah, it is. Is it possible to calibrate the sensor presented in slide 18?
Slide 18. Just a minute. Slide 18. Yes, it's possible. Actually, Professor Gailin, we have measured this hemispherical strip-based strips for monitoring various kind of sensors, and still we are working to develop this hand gloves by using that one, and the work is in progress. If you see here, spinal backside and neck, this left hand side image, neck, neutral and right and left conditions, we are able to clearly distinguish the output magnitudes. And similarly, if you see the knee movements, the magnitudes are quite different. In each and every case, clearly we can calibrate. There is no issue involved with this, but we need to reduce this thickness of the hemispherical strip. If you see here, the hemispherical strip is almost lies around a few hundred micrometers. So if you are able to reduce this few hundred micrometers, this is still more highly adaptable to the human bodies. So we are working on that one. In my opinion, the calibration is highly possible in this case.
Okay, thank you very much for your answer
and
for the nice presentation.
Yeah, thank you, Ms.
So thank you, Dr. Rao.
Yeah, yes, ma'am. Thank you. I'm going to leave.
Madam, actually, I have a question for Professor Gillian Pulavitra, if she is available still.
Yes,
Yes.
yes, of course.
Yes, Madam. So this is not really my field. I have a simple question that for your devices, I saw that in some of the devices you are using PDMS as a substrate.
Yes.
And in some other cases, you are using PET. So,
Yes.
like, is there a particular reason for using one over the other in different situations?
The reason is that PET we were using had was commercial one and had a standard thickness, and PDMS
Yes.
we are able to adapt the thickness and to study also the effect of the substrate thickness on the performance. So there is more possibilities to improve the device with PDMS.
Okay.
And also, probably PDMS introduces some additional effects that we are studying right now, because with PDMS, the performance increased quite a lot. And so maybe it's mechanical effects, or maybe it's more charging effects. So this is under study.
I have one query, Professor Gali.
Yes.
Ma'am, you are using zinc oxide for your whole works, as what I saw in your presentations. As I know that zinc oxide have a poor piezoelectricity and as well as a poor ferroelectricity. Why still working on that factor? This is a simple.
We wanted to keep a low-cost process to synthesize lead-free piezo material.
Okay.
So we didn't want to change this strategy, even if, of course, piezo ceramics and PZT in particular give much higher voltages. But at Gréement, we are trying to focus on lead-free materials. This is why we did this choice. And in fact, the nanostructure, the nanostructuration, the fact to use nanowires improves the performance compared to PZT thin layers. So finally, the performance are not so bad compared to PZT MEMS layers.
Okay. Thank you. Thank you.
Thank you.
Yeah, thank you.
Okay, madam. Thank you. Merci beaucoup.
You're welcome.
From this is the end of this session, and the next session will begin just in 5 minutes. You stay there and enjoy the talks.
Hello, everyone. I'm going to try to share.
Yeah, we can hear you.
I'm going to try to share screen. Sorry, I had a bit
Yeah,
of trouble.
Professor. Yeah.
Yes. Let me share the PowerPoint if I can. Okay, now. Can you see the slides?
Yes, perfectly.
Okay, perfect. Thanks. Thank you very much.
So many thank you to Javier and accepting our invitation, and very crucial moment we are able to connect. So this is called the advancement in functional material. This is
Yes.
a quick connection, last moment you can say. And I feel very glad to find you now. And really this is called the advancement in functional material as this pandemic situation. And I am very
You are on mute, I think.
on behalf of our honorable founder, sir, Achyuta Samanta, on behalf of our KIIT University, on behalf of our School of Applied Sciences, on behalf of our organizing committee team, and on behalf of myself, heartily welcome in AFM 2020. And I hope in this pandemic situation, when going to be normal, definitely you will accept our invitation to visit our Kalinga Institute of Industrial Technology, that's called as a KIIT University. And here you feel happy to know that our university, more than 30,000 underprivileged students are there. They are where staying together, food together, and education together from KG to PG, free of cost. This is the unique university in the whole world. Unique university, and this is a self-sponsored university, and you feel nice that all the education and underprivileged, they have no home, they have no cloth, they have no food, and this is so. Our founders are running the two parallel university. One, we are the Kalinga, and our sister university is called KISS, Kalinga Institute of Social Sciences. So if you visit India, I can say this is another heaven in the world. This is a KISS. As you see, the people do the KISS, but this is definitely the KISS on the underprivileged and the unique university of the whole world. So many world records are there, so many Limca Book of Record there. And I think by your support, definitely our two university is going to be a strong bonding in case of our functional material and the energy materials. Nice to see you on the screen. I giving this session to chair the Vaibhav Bhushan. Please, Vaibhav Bhushan.
Oh, thank you very much.
So I welcome Professor Xavier Moya on this platform. Xavier Moya is a Royal Society University Research Fellow with 15 years of experience in caloric materials. He currently focuses on electrocalorics and mechanocalorics. He has published 18 papers in Nature Science and Nature Science family journals and has an H index of 34. He is the recipient of the Young Researcher in Experimental Physics Prize from the Spanish Royal Society of Physics, the Emerging Talent Award from the Society of Spanish Researchers in the UK, and the prize in Physical Sciences from the UNESCO Universal Scientific Education and Research Network. He is also a 2019 recipient of the Global Cooling Prize from Mission Innovation. So now I request Professor Moya to present his work.
Thank you very much. Let me start thanking all of you very much for the invitation to participate in this conference. I think the work that you are doing at your university is really amazing. So I'm very happy to be giving this last lecture during your conference. Apologies for the slight delay in signing in, but I was checking the phone and I got a bit confused with the timing. But thankfully everything is working. So if at some point you see there is any trouble with the slides or you cannot see well what I'm presenting, let me know and then I will stop. And having said that, just let me start from the beginning. So today I'm going to be talking about some of the work that we are doing here at the Department of Material Science on advanced functional materials, with the focus on materials for sustainable energy applications. This work, of course, is not done only by me. It's done in collaboration with a number of people, which are listed here, especially
people in the group in Cambridge, and then collaborators in Spain and in the synchrotron near Oxford for spectroscopy and scattering experiments. So the reason I'm interested in materials, or in materials that are called functional, is because normally these materials display a phase transition. And when the material displays a phase transition, it can change the state, for instance, between being paramagnetic and ferromagnetic. And that normally gives the material a property that then you can exploit for a new application. So my research really focuses on materials that show phase transitions. And just as a general comment, as many of you will know, there are two different types of phase transitions. There are phase transitions that are called first order, which are shown here. So here you have the order parameter, which I label X as a function of temperature in this axis. And when the transition is first order, the order parameter, which can be the magnetization in a magnetic material or the polarization in a ferroelectric material, changes very sharply with temperature. On the other hand, in a second order phase transition, the transition is much smoother, is continuous. So you can see that when you change the temperature, the order parameter changes more smoothly. You can do this with changing temperature, but you can do the same by applying an external field, which is shown in the graph here on the bottom, where the field is labeled Y, and this can be a magnetic field in a magnetic material or an electric field in a ferroelectric. And again, you can see that when the material has a first order transition, you can get big changes in the order parameter when you apply the field. And if the material has a second order transition, the changes are much more continuous. Now, you can use both types of materials for applications, but normally in first order materials, because you have this very sharp change in the property of the material, and again, this can be magnetization, it can be ferroelectric polarization, it can be volume, because you have this very sharp change when you, let's say, change temperature or apply an external field, then these materials become very interesting because then you can use them for sensors or for actuators or for a number of applications. So during the talk today, you will see that I'm going to be concentrating on materials that show phase transitions, and in particular, materials that display first order phase transitions. Another interesting thing in functional materials is that when you have materials where there is coexistence of a number of properties, so for instance, materials that are at the same time magnetic and ferroelectric, then you can actually exploit the coupling that you have between these different properties in order to have something that is called multifunctionality, where instead of just having a simple function out of the material, you can get more than one function. And this can be particularly interesting when you try to make new applications that are energy efficient. My work actually is driven primarily by scientific curiosity, trying to understand how materials operate. But then in the group, we always have an interest in potential applications that can come out of these materials, and in particular applications that are useful for sustainable applications. So just a very brief summary of the things that we do in the department. We look at magnetic alloys that show magnetic ceremonial effects, magnetic superelasticity for sensors and actuators. We also look at magnetoelectric materials where you have a very strong coupling between the magnetic and the electrical degrees of freedom. And we have a special interest on thermal properties, and in particular on these materials, which are called caloric materials, that I will describe during the rest of the talk, where in effect, what you can do is control the temperature of your material, of your solid, when you apply and remove an external field. And this could be very useful for solid state cooling applications. So having said that, let me start with let me continue with the outline of the talk. So at the beginning, I'm going to give you a brief background about caloric materials and why they're interesting. Then I thought that it would be interesting for you to see a little bit of the history behind these caloric materials, because it's not very well known. And then I'm going to move to the main set of results. So I'm going to present elastocaloric effects in organic materials. And then I'm going to concentrate on barocaloric effects in inorganic salts and organic materials. And finally, at the very end, I'm going to just conclude with some interesting results that we got last year, in this case on electrocaloric systems. Now, as I said, caloric materials are materials that can change temperature when you apply and remove an external field. And depending on the type of field that you use, they have different names. So if you use a magnetic field to drive these temperature changes, these materials are called magnetocaloric, so are the ones shown here on the left, where basically when you apply and remove a magnetic field, you can make the material hot or cold. If you apply an electric field, these materials are called electrocaloric materials. And then if you use a mechanical force, if the force is a uniaxial stress, these materials are called elastocalorics. And if you use hydrostatic pressure, these materials are called barocalorics. Now, these materials are at different level of maturity, and they have different advantages and disadvantages. So some of you may know about magnetocaloric materials. These materials were discovered more than 100 years ago, and they are used in many research labs to achieve ultra-low temperatures. But they have the challenge that if you want to make a magnetocaloric device, you need to use permanent magnets, which normally give you 1 Tesla magnetic field. And this limits very much the temperature change that you can get in the magnetic material. So typically, in the best magnetocaloric materials, if you apply 1 Tesla magnetic field, you get a temperature change of around 3 Kelvin, which is significant, but is not too large. So for that reason, a lot of people around, including us, have been looking at alternative materials. And one straight solution is to look at electrocaloric materials, because then you can just use a voltage, which is very easy to apply. But the challenge here is how you avoid electrical breakdown, because the higher the electric field, the easier it is to break down the material. So you start conducting electricity, and then the electrocaloric effect is lost. But I will show you the very end of the talk that we made some recent progress on electrocaloric materials, which is actually looking very promising. And then at in the next part of the talk, I'm going to be concentrating on these two, elastocalorics and barocalorics, for the reason that they can actually show, as you will see, very large thermal changes, and therefore they are looking also very promising for applications. Now, if I want to illustrate what a caloric material is, I normally like to show this video, and please let me know if you cannot see the video playing. This is a video made with an infrared camera of just a balloon, a normal balloon you can buy in any shop. So you can see the balloon here, these are my hands, and then if you stretch the balloon very quickly, you can see that the balloon gets hot, and hot here in this video means white color. Then you can wait for the temperature of the material to go back to the starting temperature, which is purple color. And you will see that when you let the material go, the material is going to become very cold, which is shown here in dark color, in black. This, by the way, is an experiment that you can do at home. You don't need an expensive infrared camera. If you take a balloon and you put it in contact with your lips, which is the most sensitive thermometer of your body, if you stretch it and let it go, you will feel this heating and cooling. Now, the reason there is this temperature change is that balloons are made of natural rubber, and natural rubber, when you stretch it, goes from being amorphous to being crystalline. So there is a first order phase transition between an amorphous state and a crystalline state. And this releases energy. So this is why when you stretch it, it gets hot. And when you remove the stress, the material goes back to be in the amorphous phase. So it has to absorb energy from the environment, and this is why it's getting cold. And you can actually see that you can make this kind of cycle where first the material gets hot and then it gets cold. So you can actually make a cooling device, which in many ways is how we achieve cooling normally. Because if you think about it, in your fridge or your air conditioning system, what you do is you take a gas, you compress it, and then you make it liquid. So there is a phase transition between gas and liquid phase, and the material gets hot. And then when you expand it, the fluid goes from being liquid to being gas, and then the gas gets cold. So in conventional fridges and air conditioning systems, you exploit a phase transition between a gas and a liquid phase to achieve cooling. But of course, the gas is going to leak to the environment and is going to contribute to global warming. So the idea behind these caloric materials is, can you actually use the same principle of driving a phase transition and then use the thermal changes in the material to make a cooling system, but with the benefit that the material is always solid, so it's not going to contaminate the environment. And that's the main motivation of this work. Now, if you want to compare the performance of the different caloric materials, which is shown here, normally the properties that are interesting to characterize are the temperature change, delta T, that you can drive in the material, and the entropy change that you can drive in the material, depending if you apply the field very quickly in adiabatic conditions or very slowly in isothermal conditions. And in these graphs, which are basically the same The difference is that here at the top, entropy is normalized per mass, and at the bottom per volume. But you can see in the different colors, so in blue, you see the magnetocaloric materials, in green, the electrocaloric materials, and in red, the elasto and barocaloric materials. You can see that prior to 2015, most of materials were performing with temperature changes of 30 Kelvin or less, and entropy changes of 100 joules per Kelvin kilo or less. Now, these effects are very large, and these are normally called giant effects. But I want you to keep these numbers in mind, this 30 Kelvin temperature change and 100 joules per Kelvin kilo entropy change, because at the end of the talk, I'm going to show how these materials compare to vapor compression and how they compare with the newest materials that we have discovered. So just let me move to the history of in particular mechanocaloric materials, because these ones are the ones that I'm going to focus in during this talk. So actually, the first experiment ever on caloric effects was very similar to the one that I showed you with the balloon. And it was done in 1805 in the Lake District here in the UK by a scientist called John Gauss, who was actually the teacher of Dalton the chemist. So John Gauss was blind, so he couldn't do many experiments himself, but in 1803, so this is very long time ago, he got a piece of natural rubber that was actually coming from India. So the sample was coming from India, and this is why you can see actually in the title of the paper, it says caoutchouc, which is the same as natural rubber, or Indian rubber. So it used to be called Indian rubber. And he actually did this experiment of taking the piece of natural rubber, put it in contact with his lip, and then stretch it and let it go. And then he experienced this heating and cooling, but he couldn't explain it because at that time, even the concept of entropy didn't exist. So what happened is that then a few years later, Joule, which you will know because he names the units of energy, Joule was very interested in thermal properties, and then he saw this paper from John Gauss, and he said, okay, this is very interesting. I mean, it's a bit strange that a material can change temperature when you stretch it and let it go. So he decided to do some experiments, and in parallel, he sent this paper to his good friend, William Thomson, which many of you will know as Lord Kelvin. So Lord Kelvin at that time was working in Cambridge. He was an extremely good theorist. He did a lot of amazing work, and again, his name is used his name is used for the units of temperature. So you can tell that he did a lot of good contributions to the field of thermodynamics. And actually, in the 1850s, Lord Kelvin was able to break down the basic thermodynamic equations that explain why some materials show these large thermal changes and why some materials don't show them. And this is basically the same theory that we are using nowadays. So just notice that this was done 150 years ago. So very, very impressive work. The main message of this theory, and I recommend people reading this paper, it is very, very interesting and well written. But the main result of this is that he was able to say that in order to have a large caloric effect, and that means a large temperature change or a large entropy change when you apply an external field, you need to have materials that show large changes of the order parameter that I showed you before in the first slide, which I label X. So this again will be magnetization or polarization as a function of temperature. So you want materials that can change, let's say, magnetization very sharply with temperature, because that means that if the material can change magnetization by a large amount when you change temperature, if you can change the order parameter with an external field, then the material should also change the temperature by a large amount. And that's the key. And using this equation, you can actually tell that the most interesting materials are materials that show first order transitions. Because if you remember, first order transitions, so you can see it here, have a very sharp dependence of the order parameter versus temperature. And that means that this derivative, the derivative of the order parameter versus temperature, is going to be very large, close to the transition. So this is why it's very useful to concentrate in first order transitions. Now, then what happened is that Kelvin sent the theory back to Joule, and then he said, okay, so now I have a theory, so why don't you go and test it? And then Joule actually did a lot of experiments of basically stretching and letting go a lot of different materials and then measuring temperature with a thermocouple. In this table, you can see that he measured a number of metals, iron, steel, lead. He also measured natural rubber, which is here, and he also measured wood, even glass. And you can see that he actually measured very small temperature changes. So these are in the region of 0.1 degrees. So they are not useful for applications. But interestingly, the measurement was matching very well the theory. So at least he was able to show that the theory made sense. But because at that time, I mean, we are talking like 150 years ago, there was not a lot of interest in trying to look for environmentally friendly cooling solutions. This sort of remained as a scientific curiosity, and there was not much work done for many, many years. Things started to become a bit more active in the 1980s, so this is 100 years after, when people started to work with materials that show first-order transitions, because this, as I said, is when you can have very large effects. So in the 1980s, Brown and colleagues in the US did a number of experiments where they took metallic alloys, which belong to the family of Shea memory alloys. So these are alloys that are able to have very large strains of around 5 to 10%, so very big for being a solid, when you apply and remove a stress. And the temperature change associated with that change in strain is very large. So in this graph, you can see the temperature as a function of time. You can see when you stress the metal gets hot. Then you wait until you change the temperature, and then you remove the stress and it gets cold. So this is the same experiment I showed you before with the balloon, but in this case with a Shea memory alloy. And you can see that they were able to change the temperature by roughly 15 degrees. So that's a temperature change that is starting to be useful for applications, because for instance, for air conditioning systems, a temperature change of 15 degrees is what you need. So this actually started to look much more promising for cooling applications. In terms of varocalorics, in the 1980s, also there was some work on studying polymers, but in this case away from phase transition. So the effects that they measured were large, around 8 degrees, but not super large because, again, there was no phase transition involved. Then a few years later, actually, Alex Muller, who many of you will know, Alex Muller was awarded the Nobel Prize for the discovery of high temperature superconductivity. In the 90s, he was interested to develop a new cooling technique in order to cool down the superconductors and use them. And he actually looked into this varocaloric cooling near a phase transition. So he had the perfect idea, but unfortunately, the sample that he selected, which is this oxide here, was not the best material for varocaloric effects, because this material shows a transition that is second order, which is very smooth. So the effects are not very large. And actually, if you look, this is the temperature that he measured when applying pressure. You can see that the temperature change that he got, the cooling, was very small, and it was much less than 1 degree. So again, this showed the concept of let's focus on phase transition, but the phase transition that he chose was not the optimal one. That actually happened in the 2010s, so 10 years ago. And there were a number of groups in the world that look at magnetic compounds that show first-order transitions that you can drive with pressure. And these ones are the ones that show giant varocaloric effects. So normally a giant effect is an effect that shows entropy changes in the region of 20 joules per Kelvin kilo or more, and temperature changes in the region of 10 Kelvin or more. And these are two examples. Now, in parallel with the materials development and discovery, there's been also quite a lot of work on building prototypes. So these are a few examples of elastocaloric prototypes, which are actually showing quite good performance. And then in terms of varocaloric prototypes, there is not yet a varocaloric system, but we are developing a few. So this is a cartoon of one of the systems that we are developing at the moment, but unfortunately, I cannot share information with you at this time because we are in the process of filing patents, but hopefully I can show you some results next time. And just for motivation, I will say that this is actually a very interesting field to work. It's very new, this mechanocaloric field. You can actually tell from the number of publications that this is actually going up quite quickly. And in case in the room there are some Star Wars fans, you will notice that actually the increase in publications happened at around 2015, when actually The Force Awakens was released into the cinema. So I don't know if there is a connection there or not, but I leave you for you to decide. Right, so let me move into the experimental results section. So first I'm going to show you the performance of this natural rubber in a bit more detail. And again, as I said, this is something that you can do at home. And actually we do it for our reach activities a lot, of just taking the balloon and experiencing the heating and the cooling with your lips. But you can also do it in the lab. So this is a video done in one of the mechanical testing systems that we have. The balloon is here at the moment, and these are the grips of the mechanical testing machine. And you see that when you stretch the balloon, again, it gets hot, which is white color. And then you wait until the material is exchanging heat with the environment. And then you let go the strain, and then you will see that the material is going to get cold, which will happen in a second. And this is how you can make a cooling cycle. So hopefully the cooling will happen very soon. And let's see. So the video is playing a bit slowly. Yeah. So now you can see the balloon is cold when you remove the stress. So then using the infrared camera, you can get the temperature changes. So here on the top, you have snapshots of the balloon at different times. So green is room temperature, and now red is hot and blue is cold. So we measure these temperature changes, which are large. And then we wanted to understand the origin of these effects, because there were some papers in the past that said that these effects were coming from the traditional elastic spring in a polymer. But actually, by doing modeling, which is shown here on the bottom, so you can see that the modeling is matching very well the experimental results, we were able to demonstrate that in fact, in natural rubber, there are two contributions. The contribution from the classical entropic spring, which just comes from the fact that if you have a lot of polymer change and you align them, you're going to reduce the entropy, so you're going to change the thermal properties. But there is another contribution, which is this strain-induced crystallization, so this phase transition from amorphous to crystalline, which actually is much more important. And you can see this better in this plot. So this is a plot of the temperature versus time. In red, you have the total measurement from the infrared camera. And then in blue and in green, you have the two different contributions. So the entropic spring contribution is the green, so you can see that the effect is small, whereas the crystallization contribution, which is shown here in blue, is much more relevant. So at the moment, we are exploiting this information to make better polymeric materials for elastocalorics. And again, that's something that is work in progress, so hopefully next time I can share a bit more details with you. So now let me move to the valedictory section of the results. So as I said a few slides ago, in the 2010, basically after 2010, there were quite a lot of works on developing giant valedictory effects in metallic magnetic alloys, which show very good performance, but the performance is rather limited. So this is a table of the materials that existed before 2015, when we started our project. You can see that there were a few giant valedictory materials, which are shown here on the table on the left. These are all magnetic compounds, and they show entropy changes, which are shown in this column, of maximum 24 joules per Kelvin kilo, under pressures of 0.3 gigapascals, which are 3,000 bars. So these are 3,000 atmospheres. So these are relatively large pressures. So what we wanted to address when we started our work was can we actually look at materials that are not metals and see if we can improve the entropy changes, so the caloric effect, and at the same time reduce the driving pressure, because that will make everything much more energy efficient. And in the next slides, I'm going to show you a few examples of the results that we achieved. So one of the first samples that we investigated was ammonium sulfate, which is this sample here. Ammonium sulfate is a very common material that you can buy to fertilize your garden. So it's a material that is normally used to put nitrogen into the soil. And the good thing is that then you can buy samples very cheaply. So you can buy kilos of materials for a few pounds. The material comes in powder, in white powder shape. And what happens to the material is that when you change the temperature, the material goes from a highly disordered state to a highly ordered state. And you can imagine this in terms of the ammonium sulfate molecule. So if you look at the ammonium sulfate molecule here, you see you have two ammonia groups and one sulfate group, which are shown here in the unit cell. What happens is that at high temperatures, at low pressures, these molecules can vibrate between two different positions. And when you apply pressure or when you cool down the material, the ions freeze. in one position. So you can go from a highly disordered state to a highly ordered state. And this is going to give you a big change in entropy, because at the end of the day, entropy is a measure of the disorder in the material. So this is what you want. You want to change the ordering of the material as much as you can. So we took these samples, we did some calorimetry, which allows you to measure heat as a function of temperature. And then normally when there is a transition, you get peaks. So this is the graph that is shown here. So you see these peaks on cooling and on heating, which corresponds to this order-disorder transition. Then you can integrate this data to calculate the entropy of the material, which is shown in this panel in the middle. So you can see on heating and on cooling, you get big changes in entropy of around 120 joules per Kelvin kilo. And the other parameter that you need in a material for being a good barocaloric material is a big change in pressure, in volume of the transition. Because if the material changes volume by a large amount, then you should be able to drive the transition with pressure. Because when you apply pressure, you're going to stabilize the phase in the material with the lowest volume possible. And luckily for us, if you look at the volume of the material as a function of temperature, again, there are big changes in volume of around 1% in this material. So this material was very promising because it was showing both large entropy changes and volume changes. And these are the two ingredients that are useful for barocaloric applications. So then what we did is we use a calorimeter where we can apply pressure. So this is the data. So this is the heat flow at different pressures. And then you can integrate this data the very same way I said before. And then just concentrate on this graph on the right, which is the summary of the results. So this is the entropy change that you can drive with pressure, the barocaloric effect as a function of temperature at different pressures. And you can see that by looking at this system, we were able to achieve barocaloric effects in the region of 60 joules per Kelvin kilo under 1 kilobar. And if you put this in context, by comparing it with the materials that I showed you in the table before, you can see that by switching from magnetic systems to inorganic salts, we were able to increase the entropy change by a factor of 3 while decreasing the driving pressure by a factor of 3. So this is a win-win situation. And then having understood the physics behind these materials, then we started developing other interesting systems. So we also look at compounds like superionic conductors, which show also very good performance, and some other materials which are shown in this table. But what I wanted to basically concentrate next is inorganic materials, because at the end of the day, the competition is vapor compression, right? We actually use vapor compression, we use gases to achieve cooling and heating. And if you look at the typical gas that you use in an air conditioning system, which is this R134A, this is a hydrochlorocarbon. The phase diagram looks like this. So you have pressure and enthalpy. This is the gas phase on the right, and this is the liquid phase on the left. And then this enthalpy change is the one that you can get when you go from the gas phase to the liquid phase. And this is the energy that you can use for cooling and heating. So this is the competition, really. And if you look at these values and convert them into entropy changes, you can see that the typical entropy change in vapor compression is around 500 joules per Kelvin kilo, and the temperature change is in the region of 30 Kelvin. So you can actually tell that even though these materials are very interesting, they are still one order of magnitude behind vapor compression. And this is one of the reasons that we are still using gases for cooling and heating. We are not using solids yet. But this is actually changing, and I show you some of the results that we have achieved. So in order to improve the performance, we decided to start looking at organic materials, and organic materials that show very strong order-disorder phase transitions, in order to see if we could actually improve the performance on solids and bring it closer to vapor compression. And the answer is that we were able to do this. And this is just one example I'm going to show you of a material, which is this organic compound called neopentyl glycol, which is known as a plastic crystal. Now, you may be familiar with liquid crystals. Liquid crystals are made of very long and thin molecules, so you can use them for displays. Plastic crystals are similar, but the molecules are very spherical. And this is very useful because what happens is that when you're in the high temperature phase and low volume phase, the molecules are sitting in a lattice, but they are able to rotate freely. So they are rotating freely. They are highly disordered. And then when you cool down or you apply pressure, the molecules freeze. They stop rotating. So again, this is a transition that goes from a highly disordered state to a highly ordered state and gives very big changes in thermal properties. So you can do calorimetry, same as I done before. You can now see that the entropy changes are in the region of 400 joules per Kelvin kilo. And this is looking very promising because it's order of magnitude larger than the other caloric materials and similar to vapor compression. And also the volume change is very large. It's around 5%, which for a solid is really gigantic. So then you can do the same experiments of calorimetry versus field, and then just concentrate on the graph on the right, which is the summary of the results. So this is entropy change that you can drive with pressure. So this is your barocaloric effect versus temperature at different pressures. And then you can see that in these organic materials, you can get entropy changes in the region of 500 joules per Kelvin kilo, which is comparable to vapor compression. So you can see this comparison better on this graph here on the left. So this is the maximum entropy change versus pressure. In orange, you have vapor compression fluid, the one that I showed you before. In red and blue, you have the material that I'm showing you now, this organic plastic crystal. And in green, you have all the other caloric materials that I showed you before. So this was very exciting for us because when going away from inorganic materials and concentrating on organic systems, we were able to increase the performance by an order of magnitude, and for the first time bring it to something that is close to vapor compression. So what we did is we patented these materials and other materials that are related to them. And then we also started a spin-off company collaborating with a couple of major refrigeration industries and building the prototypes that I said at the beginning. So this is work in progress, but hopefully in the next year we have some exciting results to share. And just to finish, if I have a few more minutes, just let me finish with something slightly different. So I'm going to tell you a little bit about electrocalorics, because last year we had actually a very interesting result. And I thought also, given that the previous talk was on piezoelectrics, that you may be interested in this. In electrocalorics, as I said, the problem is that the effects are proportional to the electric field. So you want to take a dielectric material and apply a very large electric field in order to have a large temperature change. But the problem is that any dielectric, if you apply a very weak electric field, at some point it's going to start conducting, and then any electrocaloric effect will be destroyed. And this is when you achieve the electrical breakdown. So a solution is to work with very thin dielectrics, because in thin films, in thin dielectric materials, the breakdown field is very large because it scales as 1 over the thickness. Now, if you use a thin film for electrocalorics, you are going to have a very large thermal change. But if you have a very large temperature change in a 10 nanometer film, that's not going to be useful for cooling, because if you're trying to cool your apple, which is this big, with a 10 nanometer film, the thermal masses are very different. So the solution is to look at multi-layer capacitors, where basically you have a stack of a lot of thin film electrocaloric materials, one on top of each other, so you can exploit the fact that the individual layers are very thin, so you can apply a very large electric field. But because you have many piled on top of each other, you can also have a big object, a macroscopic object, so you can actually achieve some real cooling. Now, multi-layer capacitors are not something that are new. They've been around for a long time, and in your phone and your computer, you have hundreds of them, because normally they are used to store charge. If you look, for instance, this is a CPU from Intel. This is a picture of a capacitor that is made of nickel electrodes and barium titanate layers. So barium titanate is the prototypical ferroelectric material. You can then see that if you can replace this barium titanate by a good electrocaloric material, hopefully you get something that is promising. So this is something that we and others have been doing for quite some time. So in this graph here, you have the temperature change, the electrocaloric effect, as a function of the operating temperature and as a function of the electric field. And you can see that despite there's been quite a lot of progress, before last year, the performance of the best multi-layer capacitors was below 3 degrees. So what we wanted to do is see if we could improve the performance of these materials. And then we look at a very interesting material, which is lead-scandium tantalate. So this is a ferroelectric perovskite. You have the standard perovskite unit cell, but you have this ordering of scandium and tantalum atoms, and this gives you a first-order transition with a large latent heat, a large change in energy, which is very useful for electrocalorics. And moreover, when this alloy is fully ordered, so you have the scandium and the tantalum in juxtaposed positions, the electrical breakdown is also very high. So what we did in collaboration with our collaborators in Murata, which is the largest manufacturer of multi-layer capacitors, we made these multi-layer capacitors made of let's scan the tantalate, which here I call PST. And then we test them again with the infrared camera. So this is a picture of the infrared camera when the capacitor is cold. And you can see that the temperature changes are very large, are in the region of 5 Kelvin. And you can see this better on the graph on the right. So this is the temperature change as a function of the operating temperature. And you can see that in this multi-layer capacitor, we were able to get temperature changes as large as 5.5 degrees, which for electrocatalysis is a big step change, is a big development. So if I plot these materials in the same graph that I showed you before, you can see that at room temperature, which is where you want to develop these materials, we're able to achieve much larger effects. And even more interestingly, you can see that actually these peaks in temperature are very, very, very broad. So you can see that you can get a big temperature change over 100 degrees. And this is very useful because for applications, if you only have a big temperature change in an interval that is only 1 degree, you're not going to be able to make a useful prototype. So just for comparison, if you compare these electrocaloric materials with the performance of gadolinium, which is the prototypical magnetocaloric material, you can see that we can actually get larger effects than gadolinium and over a much broader temperature range, which are two benefits for any prototype. So we published this paper last year in Nature, and actually we are hoping that these elements, these multi-layer capacitors, are going to start being used in a number of prototypes. So having said that, let me get to the conclusion. So this is more of a summary. It's more of a summary than a conclusion, but I just wanted to say that this is a very new area of research, and is very. There are many things to explore because there is a very fertile playground of materials for mechanocaloric effects, for both elasto and barocaloric effects. So for somebody that wants to join this area of research, there are many materials that haven't been studied yet. So there is plenty of room to do work in terms of materials development, materials performance, measuring techniques, and prototypes. So you can work in a number of areas. Hopefully I gave you a few examples of interesting materials. So in particular, I show you giant effects in organic elastocaloric materials and much bigger colossal effects in organic plastic crystals. And just let me finish by saying that, yeah, I mean, this is a very new area of research. It has plenty of scope for improvement. And hopefully, besides addressing some interesting science, some interesting applications can come out of this. And this is very critical because at the moment, if you look at the energy balance in society, for instance, in the UK, 40% of the total energy consumption goes into heating and cooling. And this is very relevant because normally people tend to talk about, let's say, production of energy using solar cells or storage of energy using batteries. And these are very, very important. It's important to do development there. But I just wanted to point that heating and cooling actually corresponds, it represents the largest contribution of energy because everyone is cooling the fridge at home. And then in the winter, you are heating your home, and in the summer, you are cooling it down with air conditioning. So this represents a very big proportion of the energy consumption, and we are still using a very old technology because vapor compression was developed 100 years ago, and it's more or less the same. I mean, it hasn't developed that much. So I think it's about time that we find, hopefully, a better solution for heating and cooling that is friendly to the environment and also more energy efficient. And with that, I thank you very much for your attention, and I'm very happy to take any questions.
Thank you, Dr. Xavier Moya, for such a nice presentation of your work. So this is time for some questions. If anybody like to ask some question, they can raise hand or type the question in chat box. So here is a question from Sushmita Dey. Did you try for high entropy oxides for electrocaloric cooling?
Well, what do you mean by high entropy oxides? If I can ask.
Okay, sure. I would like to unmute Susmita Dey, and she will ask her question.
Thanks.
So Smita Day, you can unmute yourself. Okay, let me ask another question.
Well, if not, let me say something because maybe
Okay,
this
she has
helps.
unmuted.
Okay.
Yeah, she has unmuted. Now she can ask. Shusmita, you can ask your question.
Yeah, very good evening, Professor Moya. Actually, there are recent papers now. People are also investigating this rare earth high entropy oxides for this electrical application. So I was just interested, like, if your group is working on this aspect.
I see. So no, I don't think we are. We've been doing. I'm trying to see if I have some slides. We've been doing a lot of work in traditional oxides. Sorry, I don't have any slides. We've done a lot of work in perovskites. So barium titanate, lead manganese, lead niobate, PMMPT, all the traditional oxide ferroelectrics, which I don't think are high entropy because entropy changes are rather small. But thanks, I will take a look at the oxides that you were saying.
Yeah, thank you. Can I?
Susmita,
Yeah.
For your information, I'm reading in India, Professor B.S. Murthy from Director of IIT Hyderabad
Yes, sir.
is
Yes,
a
sir.
renowned person working the high entropy alloy in the
Yes, sir.
international forum. And India, I can say, the first person to work very nicely high
Yeah.
entropy alloy. So any kind of, if you want high entropy alloy or oxides, it's a combination of more than 5 oxides and thermodynamics follow, then you can say the high entropy oxides. If you want further any discussion, send a mail to me. I'll connect to Professor B.S. Murthy or other person in the world who work on the renowned high entropy oxides. And last year we have organized the very good conference for ISPAN, and who are the, you can say, the many founder of the high entropy alloy is the professor from Japan. So sometimes if you want any information on high entropy alloy or oxides, any kind, just drop a mail. I connect you the people who are working in the world. Thank you.
Thank you. Yeah, thank you very much for your offer.
Thank you, sir.
I will take a look and certainly see the email. Thanks. Yeah.
I have one more question. Can I proceed?
Yeah.
Okay.
Yes,
So,
sir.
yeah. Okay. Thank you. Just I wanted to know, like, in your group, I think you are exploring this shape memory alloys like nickel, manganese, indium. You have mentioned now. So this alloys are also known for this martensitic transformation as well as this intermartensitic transformations. So did you carry out any investigation like correlating this intermartensitic transformations like the modulated martensite phases with the magnetocaloric effect? Like, did you establish any relationship here?
So at the moment, I'm not doing a lot of work on magnetocalorics. I used to work a bit more on that a few years ago. I think there's been some work. I think there's been some work on the intermartensitic transition, but I guess the challenge is that normally, in order to have a large magnetocaloric effect, you want to have a transition that shows a big change in magnetization. And typically, the intermartensitic transition shows a relatively small change in magnetization. So I suspect the effects are not going to be as large as with the traditional austenite to martensite transition. But if you can identify some intermartensitic transition where the change in magnetization is significant, I say it will be interesting for caloric effects as well. Yeah.
Because there are papers which report like if your sample has intermartensitic transformation, then you have chances to broaden this working temperature span. Because in case of this crystalline materials, what we have seen that either you get a very sharp entropy change, but you are limited to this narrow working temperature span. So any like work you're carrying out to solve this issue?
Yeah, I mean, it's not something, because at the moment we are concentrating on mechanocalorics and electrocalorics, but I know that, yeah, I mean, that there are many groups in the world working on magneto. And what you're actually saying, yeah, I mean, it makes sense. I mean, because at the end of the day, I show it a bit with example of gadolinium. So you don't want just to have a very large peak temperature change in a narrow temperature range. You need to have a broad peak in order to make an application. And then looking at, for instance, high entropy metallic alloys, so magnetic alloys is useful, or looking at, yeah, I mean, martensitic transitions that are not so sharp is also useful, yeah. So it's something, I mean, I'm sure there are groups in the world looking at the intermartensitic transition as well, but it's not something that we are doing ourselves at the moment.
Yeah, thank you, Professor Ma. Actually, my PhD topic is based on this. I actually worked on the shape memory alloys, nickel, manganese, copper, gallium alloys, and I tried to correlate this intermartensitic transformation with the MC properties, and we were like quite successful. Like, if you're interested, like I can share my work with you later.
Yeah. I mean, if you send me an email, I certainly will.
Yeah. Thank you, Professor Ma.
Thank you for the questions.
Thank you for such interactive session. So if any other question? There is no other question. So I thank Professor Moya for giving such a nice presentation. Thank you.
Thank you very much for the invitation, and yeah,
Thank
hopefully
you,
next time we can see
Javier.
each other in person.
Wonderful talk, and I hope the participant and many people from all over the world, people are listening you, because your program is going to live YouTube channel also. So many people are listening and getting excited from your talk, and different very good message for you. Nice presentation. Many our chat box or others have filled completely with a good essays and good and nice presentation, and hope in future also we'll have such kind of talk, even lockdown period or may pandemic situation, because this our COVID-19 give a new idea how to connect the world in a short span of time. So I think this process will continue in future, even world is going to be normal situation, even though I think this will play a very important role. And can you highlight some things? What is your opinion? Some functional material can play important role in the COVID-19 situation to cope up. Are you thinking something people are working in your institute or something? Can you give some?
Right. Yeah, that's
how these oxide materials.
Yeah, I think that's a very
in your
interesting
department, others.
Yeah, so there is actually a lot of activity in the UK related to COVID. Most of it, of course, is to do with the development of vaccines. But I can see materials playing roles in the future. So, for instance, I can imagine some materials that you can use for coating surfaces. So then the surfaces can make sure that the virus doesn't survive so long. Because as you know, at the moment, one of the assumptions is that the virus is actually transmitting through hard surfaces, through tables and desks and so on. So if we can, or somebody can make some coating that can sterilize surfaces, that will be useful. And then I guess, I don't know, I mean, I guess the possibilities are very much. I mean, nowadays, as this is proving at this point, we are moving away from traditional conferences to online conferences. So any material that goes into computing, into making communications faster and more efficient and better, I think are also going to be playing a very important role in the years to come. They were going to play an important role anyway, but I think with this crisis, all these things are being amplified.
So, Javier, can you, in concluding remarks, what is the message you are going to give to the young generation?
Right. Okay.
From a research point or next generation thought, so that the whole world get excited. Maybe in future, nobody knows that from your laboratory something will come out, a new things that will give a new insight to the whole world. Can you give some focus for the young generation people?
Right. So yeah, let me say. So materials are actually very, very important for our life. I mean, if you look actually at history, the different ages of humanity are actually labeled after materials, right? We have the Stone Age, then the Bronze Age, the Iron Age. So really, material developments have been really key for the development of society. I will say that last century was possibly the Silicon Age, because we have all this revolution on electronics and communications. But I think something that is very important to tackle now, and this is for for us, but especially for the younger generations that are coming with new ideas, is to tackle the energy problem. Because now with the COVID, we are forgetting a little bit about global warming and climate change, but this is a very, very crucial thing that we need to solve now. And I think materials are going to play a really important key part on that. So I will argue that this century is going to be the century for materials for energy. So I will say to the junior generation, if you are interested in science and you want to understand how materials work and try to find new applications, just come and join the community. It's a very enjoyable thing to do. It's very rewarding when you understand new things and when you discover new things. And I think we all of us need to contribute to look for better solutions for energy conversion, for energy storage, for energy usage. We need to look for materials that allow us to go more and more towards environmental friendly solutions. And I think this is the time to do it. So, if you're interested now in functional materials, I cannot see a better time in history to be working on this.
Thank you, Javier. I hope the message what you given just now, definitely people will look forward, and young generation, because what we're working, then now it is need for the society to look a new direction of thought. The thought what we are thinking 1 year before, now thought is changed, because we have to come out this pandemic situation and broader challenge and bigger challenge we have in front of us. So only the young generation can solve this bigger challenge. So that message what you spread now, this is going to revolution in the whole world as in functional materials. And you are the correct person. And we are going to, after a few minutes, we are going to have the valedictory program. And it will be nice if you can stay a few minutes more with us, so that
Sure.
you can have a talk in the valedictory session.
Sure.
Thank you. Within 5 minutes, we are going to start, and validity program. I also request if Golian is ready, available in the screen, I request also to be joined with us. Professor Golian?
Yes, I am here. Yes, of course.
Yes. So nice if you can stay a few more minutes in the validity program, and we are going to declare the Young Scientist Award this time. So it will be a great pleasure if both of you can join in our panel also in the validity program. So thank you very much.
Now I request Dr. Shweta Padma Prehraj, Associate Professor, Department of Physics, KIIT University, to start the valedictory session.
Good evening to everyone. So after 3 days of rigorous technical sessions, which were very interactive also, we have landed up in the valedictory function. So now I request Dr. Maya Devi, Assistant Professor, School of Applied Sciences, KIIT deemed to be university, to summarize whatever happened in all those 3 days. Ma'am, please.
Thank you, ma'am, for your kind invitation. I welcome all of you to the valedictory session of this AFM 2020. So in these 3 days, we had the workshop on the first day, and the next 2 days were the conference. So in total, in the 3 days, we had 17 speakers spoke on the different fields. So the first day, first session, it started from the first day, first session, and it was given by, each session was having a minimum 2 speakers. In the first day, the first session was given by Dr. Amitendu Rai from IIT Bhubaneswar, and he gave a brief introduction about the concept of dielectric constant and the explanation of electromechanical coupling. And from there, he moved to the fundamentals of piezoelectric and ferroelectric materials and explained about the various applications of them. So this was the first talk of the first session. The next talk was by Dr. Balram Sahu, who also gave another plenary talk afterwards. So he briefly explained about the classification of different materials based on the on their band gaps, and explained about the external effect of the external field on the materials. And he elaborately talked on the effect of laser, which gives rise to the nonlinear effect, and explained about the origin of polarization in the materials due to the effect of lasers. And he gave an overview of effect of electronic interband defects also in the nonlinear optical absorption. In his plenary talk, he gave the overview of the effect of the defect states, and in the nonlinear absorption process, the parameters affecting the nonlinear absorption processes, he explained very nicely with the example of 5 different materials which are worked in their laboratory. So this was the talk given by Dr. Balram Sahu. Then in the second session, our speaker was Dr. Amiya Priyam, and he gave a overview of the application of the semiconductor nanocrystals in our everyday life. So he very nicely explained all the phenomena related to the nanocrystals in terms of the simple physics. And he explained in his starting talk, he explained about the quantum confinement, and he related this to the confinement of the electron in a one-dimensional box. And then he moved to the explanation of the excitons based on the which are very much essential for the formation of the quantum dots in terms of the theory followed by Bohr's model. And then he explained how the color change and the absorption spectra change occurs in the structure when we go to the nanoscale. And in his plenary talk, he explained about the 2 novel methods or new methods of synthesis of the silver nanoparticle, hollow silver nanoparticles, and how it is modified to silver nanocubes with the effect of folic acid, and how the spectra is enhanced from the UV range to the NIR range by doing these modifications. He explained very nicely, and its possible application in photocatalysis he also explained. So this was the talk given by Dr. Amiya Priyam. And the next speaker was Sovan Patra, who gave an overview of excitation of the semiconductors by the incident light and how band gap can be tuned. He elaborately explained about the colloidal synthesis method of CDT quantum dots and its possible applications in solar cell and quantum computing. He also gave a brief idea of the e-learning courses offered by Tata Steel. So this was our second session. Then the third session, the talks were given by Dr. Alluri Nagamaleshwar Rao and by Dr. Ashok Kumar. And Alluri Nagamaleshwar Rao gave us a brief journey of 150 years journey of piezoelectric effect, and explained the techniques of thin film preparation and the techniques of the study of their properties. And then he moved to the device applications, how we can make devices using those. So he explained about the design of devices and the piezoelectric nanogenerators, and explained about the formation of the self-power devices like the self-power sensors and self-power NTC thermistor. He had a plenary talk today. And next speaker was Dr. Ashok Kumar, who was the principal scientist of NPL Delhi, and he in his first talk gave the theoretical concept of field-induced strain and the field device in and out of plane device configuration, Jan piezoelectric effect on the PMN and PTSI system, and the parameter controlling for sensing and actuating properties. And he explained today in the plenary talk, he explained us how we can make the low cost device, how he made the low cost device for the measurement of blood pressure in his lab, and it's possible applications for the measurement of blood pressure. So this was the talk given by Dr. Ashok Kumar. So after that, our fast day followed by the presentation of all the young scientists. So that was all about our fast day session. Then the next day, second day fast session, we had again two talks. One was by Professor Sabu Thomas, who elaborately explained about the nanocomposites and the classification of nanocomposites in terms of their aspect ratio and the importance of the points what are to be considered during the working with polymers. He explained about the various methods of fabrication of aerosols and CNT polymer nanocomposites and their applications in various fields like sensors and biomedical applications. So this was the first talk given by Professor Sabu Thomas. Then that was followed by Dr. Prasanna Kumar Sahu, who explained about the design of 2D lateral heterostructure and arranging them in particular order for possible optoelectronic applications. He explained about the TMD heterostructures in details and its importance and method and mechanism of growth of TMD via CBD method. This was his talk, and how the optical properties are affected by the layer stacking of these substances. So this was the second talk given by Dr. Prasanna Kumar Sahu, then followed by the talk of Professor Patrick Gilman, who explained elaborately and who explained an elaborate and interesting talk on the energy storage and retrieval. He explained about high energy density storage device and explained about the design of storage vessels and design of hybrid transport thermal cells for improvement of efficiency of batteries. So this was the talk given by Professor Patrick Gilman. Then the next talk was given by Dr. Dipti Sahu, and he explained, he gave a brief idea of room temperature multiferroic properties of rare earth dope, holmium, cadmium, and seed of BFO ceramics. He explained briefly how the properties change with the different, the doping of the different rare earth materials. So this was the talk given by Dr. Dipti Sahu. And then the next talk was by Emery Eden, and he explained about the point defects in ceramics and the role of it in the supercapacitor devices. He explained about the concept of EPS spectroscopy and how the basic interactions are responsible for the determination of several parameters like fine structure, G factor, zero field splitting parameters, and how these parameters can be measured directly by the EPR experiment and how these are applicable in the supercapacitor batteries, that he explained very nicely. So this was our talk of second day, second session. Then the second day, third session talk was given by Professor Ram S. Katiyar, who explained about the progress of novel single phase room temperature multiferroics. And he explained about the challenges in design of room temperature multiferroic materials and elaborately explained about the ceramic sample preparation techniques of complex oxides like PZT with PIT with with PFT and PFN and PFT. And he also explained about the thin film preparation by PLD method for PTPD and PZTPD, and there are possible applications by studying their structural properties, dielectric properties, and magnetic properties. So this was the talk given by Professor Ram S. Katiyar. And then today our session was having the talk of Dr. Hari Srikant, who gave a brief idea of magnetic anisotropy and explained about the anisotropy nanoparticles for biomedical applications. he explained about the application of nanoparticles in targeted drug delivery and explained briefly about magnetic hypothermia and how the size of nanoparticle is important for several medical applications. He explained very nicely. And then the second session was given by R.L. Sarma, who gave a brief idea of energy storage for present and future prospects. And he gave the idea of solid state batteries and its challenges for future general applications. And then next talk was by Dr. Gulian Pauline Fitteran, who explained about a low temperature synthesis method of ZNO nanotubes and its integration for several applications. And next talk was by Dr. Somdat Mukherjee, who gave a brief lecture on gallium ferrite nanostructure synthesis and their property study in the ferroelectric memory applications. And the last talk that we have got is from Professor Javier Moya, who explained about the various advanced functional, how to study the advanced functional materials for sustainable energy applications. And he explained very nicely with the example the caloric effect and how the giant caloric effect and giant barocaloric effect and how also the colossal barocaloric effect we can study, and we can use them for the study of the materials which are suitable for the sustainable energy applications. He explained us very nicely. So these were all the talks that we got from all the speakers, and it was very, very interesting and useful too. I hope it is very, very useful to all the participants. So with this, I come to the end that we are thankful to all the speakers, and we are graced to have all of them as the speakers in our event.
Thank you, ma'am. That was a great summary. Now the event, this mega event would not have been possible without our organizing committee, who have been working day and night for making this a success. And now among them, we have 3 such members, Dr. Gopal Krishna Pradhan, Dr. Gorky Shah, and Dr. Sutanu Mangal, who have been the members behind our digital team, all the online YouTube streaming and the Zoom, etc., whatever digital coordination we had, it has been done by them. So I would request them to share their experience during this 3 days conference. So may I request Dr. Pradhan to share his views first?
Thank you, madam. Can you hear me?
Yes.
Yes,
Yeah.
we are here.
Yeah.
Yes.
Good evening, afternoon, morning, depending on wherever you are. As you know, we had this event for the past 3 days. And for the university like us, it's actually, which is well equipped with excellent infrastructure to organize such effect. But given the situation that we have right now, we have taken this challenge to actually, put up this in the most efficient manner. And we had a very strong group, including Dr. Gorkisa, me, and which is led by Dr. Sutanu Mangal. And we had to work from home because of the social distancing, etc. And our actually objective was, it was very clear from the beginning that we decided to have the motto was, we should have 0 disruption and maximum impact. That was the motto with which we started working. And so I think we have been successful in achieving that. We had more than 1,500 registrations after the call was actually open. And there were about 300 participants from 300 institutions and 22 different countries. And as you know, this event is being live streamed on YouTube. And a few minutes back, our leader, Dr. Mangal, shared with me the metrics from YouTube, which we thought of actually, using this for future organization of such events. And I can actually highlight few things that we had about 4,000 viewers watching it on YouTube. And there is some interesting metrics that about 42% of the audience on YouTube were in the age group of 24 to 32. So which means we get an impression that the young people, basically these are the research scholars and PhD scholars. So they prefer to watch it on YouTube, and that's 42%. And there were about 5% people from Europe and 2% from Korea and about 3% from Bangladesh, etc. And most of the participants are from India. And we had to work actually in absolute coherence and in synchrony. And as you probably noticed that the event was, we did not see any disruption. And we have to work from our own, own locations. So, but overall, I think we have been quite successful in organizing this, putting up this show. And as you know, that the participation in terms of the students, their involvement and activity is something really very encouraging. And I hope this would, provide additional impetus for me and the team and the organizers and the conveners to organize many such events in near future. So I think with this, I thank you again for actually giving us this opportunity to put up this show. Thank you again.
Thank you, Dr. Pradhan. So may I now request Dr. Mangal to show up and share his views.
Ma'am, Gopal sir said on behalf of all of them.
Okay, okay, fine. So he has represented the team. Okay, fine.
Yeah, they asked me to do it. So yeah.
Okay, fine. So then now I request Dr. Dibyaranjan Raut, Associate Professor, as well as the co-convener of this mega event, AFM 2020, to share his views and ideas with us. Sir. Sir, please unmute yourself.
Thank you, madam. A warm good evening to all present in the valedictory session. Honorable dignitaries, honorable chief guest Dr. Ashok Kumar, honorable guest of honor Dr. Balram Sahu, honorable Dean, School of Applied Sciences, Professor Pushpalata Pattajoshi madam, and convener Professor S.K. Parasar, co-convener Bhavya Bhushan, my technical committee members, digital team, and respected invited speakers across different countries, and particularly the participants, research scholars, and MSc students. Personally, I have benefited in many aspects because I have been working on functional materials since a decade. From 2001 onwards, I have been working on functional materials, and the conference theme is on advanced functional materials. I have been listening to the speakers, very good speakers, I can say. Very informative talks were there. So I personally benefited by listening to them. Then my group also, I hope my group also benefited because my group concentrating on piezoelectric materials, lead-free multiferroic materials, as well as polymer nanocomposites. So the talks definitely benefited my group members also. And as a coordinator of department physics, most of my faculty members, they are working on material science, advanced materials for different applications. Some of them are working on thin films, single crystals, and some of them working on solar cell applications, photocatalytic applications, and also some of them like our convener, he's working on energy storage, energy harvesting. And so around 80 to 90% faculty members, they are working on functional materials. Definitely, they, by listening to our knowledge speakers, and as they have shared their experience and wisdom, so we have greatly benefited. At the same time, I hope the participants across different countries, and particularly the research scholars who are newly starting their research, and MSc students, they definitely got motivated by listening to our speakers. So it is a well planned and well thought conference, though it is first we have been done in a virtual platform. Still the coordination and the way we have conducted the conference, I think it is, we can say it is exemplary to many. So in future, some ups and downs, if it happened, some discomfort if you have feel, then on behalf of my department, on behalf of my organizing committee, I feel very sorry. So in future, we'll take care of those things, and in a better manner, we'll organize the things. And seeing the encouragement, the patience hearing from our participants, we are very much encouraged to organize such type of events in future. Seeing the participation, like it's 1600 participants from, as Dr. Pradhan mentioned, from 300 institutes and 20 different countries. So we are very much motivated and encouraged to organize such kind of mega events in the near future. And I always expect this such kind of cooperation from you all. Thank you.
Thank you, sir. So this event will be incomplete if we don't share the experiences of the participants. So if anyone is interested to give a feedback, then they may raise their hands. We can take 2 or 3 feedbacks. They can share the experiences if anyone wants to share among the participants.
There was one student, Lipsa Mishra. I saw very active participation from her. I don't know if she is there. Could you please unmute her?
Lipsa Mishra.
Yes, ma'am.
Yes.
Can you hear me?
Yeah, we can hear you.
Good evening, everyone. My name is Lipsa Mishra, and I'm a research scholar at IIT Patna. I'm working under Dr. Manas Kumar Sarangi. I'm working on photophysics, basically my field of research, and I use various nanomaterials. So in this type of conference, basically the AFM 2020 organized by KIIT is very helpful for me, and that gives a platform for a young researcher like me, and to interact with the senior and expert professors. So from the first day only, Dr. Balram Sahu, that he put lights on basics of 2 photon absorption and 3 photon absorption, and moreover he explained also the top reason, and these are basic things to understand in my field. So those are helpful for me to understand many things. So next, actually, a talk by Dr. Amir Priyam sir. He actually talked about the core cell quantum dots and all. So I have started working on this field. So this gives me very motivational speak to that I will definitely help in my research. And all are very informative lectures. No doubt there are some talks also there that are not in my field, but also I get motivated by their talks also. Today only, Professor Srikant, he inspired all of us, that he shows a innovative bio application on the cancer cell by using nanoparticles. So I can plan my research in that field also. So this conference actually gives me a glimpse of my research area, and also I am highly thankful to the organizing committee to organize such an informative program. And thank you all. I hope we could attend such seminar in future also.
You are from IIT Patna?
Yes, ma'am.
Manas Sarangi,
Yes, ma'am.
right?
Yes, ma'am.
Okay, he is a friend of mine. Okay, anyone else from the audience? Anyone else would like to say?
I think someone raised a hand.
Yeah, Ketan Kumar.
Kumar is actually asking to unmute. Gotki, could you please unmute him? Because right now I don't have access to this.
Okay, let me just unmute it. No,
Ashok Kumar.
Yeah, I have asked to unmute.
Yeah. Ketan Kumar, he has raised his hand. Perhaps he wants to share something.
Hello. Hello.
Yes.
Hello. Am I audible?
Yes, you are audible.
Yes. I'm Ketan Kumar Gaikwad from Mumbai, KG Somaya College of Science and Commerce, Mumbai. This conference by KIIT University was really excellent and wonderful. Each and every session was fruitful for us, particularly piezoelectric effect, pyroelectric effect, etc. Also, a few lectures on batteries, etc. All these lectures was very nice, and congratulations to all the team of KIIT for arranging this, for completing and arranging this workshop. Thank you.
Okay, I see another hand raised, Ananya Kumar Mishra.
Yes, ma'am.
Yeah, can carry on.
Good evening, all the members of KIIT University and other dignitaries. Basically, I was a student of KIIT +2 Science College during my +2, and now I am pursuing my graduation in Government Autonomous College, Raulkela. I'm really very happy to see your arrangements and excellent work for the betterment of all students and all faculty members who are researching on nanotechnology and nanoscience and nanomaterials and all that important aspects of physics. And basically during this situation where science and technology needs to be get advanced, and for the advancement of this IT technology, by using this IT technology and by using this video conference method, you have shown us it is the I think India's first international conference. I think it is first international conference of India virtually. Thank you so much, sir.
Thank you. We have the privilege of having Dr. Ashok Kumar from National Physical Laboratory. He has been with us all these 3 days. So may I please request him to deliver his address, and then we'll go for the release of our e-abstract book. Sir, please.
Hello.
Yes, sir.
Hello. So you people are waiting. Actually, I just went out. This is my time to talk. I am Dr. Ashok Kumar.
Yes.
Yes, sir.
Okay.
Yes, sir.
Okay. So good evening to all of you. And first, I'd like to congratulate Dr. Parashar for such a nice and wonderful conference. If you have looked the entirety of this particular conference, it covers like almost entire dielectric, ferroelectric, piezoelectric, pyroelectric, superconductivity, electrocaloric. My colleague and friend, Dr. Javier, Thank you for here. Thank you. Thank you. And it's nice to be, the part of this conference. So, and then I would, you can have, if you have looked the abstract and the audience, it's enormous. I think and the depth of the presentation by various dignitaries it's marvelous. If you have looked, this is very useful for the young people who is the first time, or I don't know, maybe some senior people also learn from, because as a scientist every day you have to learn. So we learn also a lot from young people, like young scientists. I have been there for around 1 to all 18 young researchers, which maybe our organization committee will announce award also. So this was such a wonderful event. Our Guruji, as well as many people, many dignitaries, Balram Shahuji, they have done marvelous job. And apart from Bhavya ji and all, I would like to also thanks the better half of Dr. Parasar, Kajal ji. She is, every time inspiration for us. So that's an inspiration for Parasar ji also, because we have he is always back up us. So that's the good point and great point to deliver us also. So these are the things that and the content of the conference, I can say unique in the I have been when I left USA and I joined here in 2012, and since then I have been every year at least 10 to 12 conferences here and there, international, national, this and but this time I am really happy to see the entire community, material science, like devices, COVID situation, many other aspects of the life. Like I've been also working. I did little bit hard work in order to understand the blood pressure and other things. This I am also working. So I decided to go in another aspect to talk, which is a little bit different from the. So that will also help the young generation to understand the requirement and the utility and the test procedure, as well as their day-to-day life requirement. So overall, I can say it's excellent and extraordinary research work, and the organization, as well as the conference. Everything was. I don't see any kind. If you ask me, like where are the you can find some sort of the drawbacks, I hardly see any drawbacks. So that's the beauty of this particular conference. So with these words and whatever the respect and our friendship, or you can say whatever is with entire KIIT community, is exceptionally, always I am always with it's I feel like whenever I used to go KIIT or meet with Parasar ji, Kajal ji, always feel like I am, it's not two family. We are a single family, and this you need for research, because without that, either with your student or with your family member, if you have the love and affection, your output will be many times more than in the normal way. So these are the things that I learned. Again, I would like to congratulate, and I would like to many thanks entire KIIT family with such a wonderful conference, such a wonderful organization, organizing this particular conference, and I can say it's exceptionally excellent. So that's my views and my comments from my side. Thank you very much for giving me this opportunity to talk, interact with these people. Thank you very much. So
thank you so much, sir. So now we'll go forward towards the release of our e-abstract book by our chief guest.
Okay, so let me share this. I'll start this. So I am sharing, and in this way it will release. So this is the new world. So now this is already open to all. I have shared the screen to all of you. I think this is fine. E-abstract is with us now.
So, sir, can we just maximize the screen? Okay.
Yeah,
That's
yeah,
yeah.
yeah. Everything is going on. I am just increasing all the things. This is the, this is the. Let me go one by one. That will be a good way to release the things. I am going. So this is our AFM 2020 e-abstract book, and this book is also yeah, this will tell you the beauty of this particular conference. I also like to congratulate the chief patron, Professor Achyuta Shamanji. Such a wonderful organization he has created for the Indian community or international community, you can say. And I would also like to tell this moment, if anyone having any time to visit this particular institution, you must go KIIT and KISS also. Wonderful. I was there once upon a time. I wish to visit again over there. And that's the one of the best institution I have ever seen in my life. So you must visit KISS, whoever with and I would like to request all my foreign dignitaries and colleagues, whenever you have time, you visit India, you must visit there. You will see how good this institution is, how is the social services there. So this is the advisory committee of this particular conference. And apart from this, you can see here convener Parasarji and the chairman, all patron like Subrata Kumar Acharya ji, Mohanty, Shashmita Shamanji, K. Mohanty. I don't know all these. You can have look all dignitaries, which is the scientific committee, convener, chairperson, co-convener, organizing committee. I don't know whether I have to explain everyone. International community. Invited speaker, you can see here a list of invited speaker from all over world, from United States, from the UK, from Nambia, from France, from South Korea, Istanbul, many. It's covered like Australia, everywhere you can see here. So this is the beauty of this particular conference. uh, mm, Again, so I would like to message from the patron. You can have look message from the from many dignitaries, vice chancellor of the KIIT, from message from, you can have go through the Shashmita Shaman, pro vice chancellor of the university. You can go the functional material, Mohanty Shah, and then you have a message from Patto Joshi ji, Dean of the KIIT Deemed University. Then, of course, all in all, I can, again, I would like to congratulate Parasa ji for such a wonderful conference, convener. Then these are the list of the various dignitaries. You can go one by one, you can have look the different uh, essence of this particular conference, where I think everything is covered. Most of the thing from the spintronic, resistive switching, either you can do electrocaloric, piezoelectric, pyroelectric, ferroelectric, of course, that is a part of everything. Magnetism, magnetoelectric. I can see everything. So this is the you can have go many posters like 1500 more than I Parasaji convey me here 1418 papers has been submitted for this particular conference. And of course many you can see invited talk abstract from various dignitaries, from various authors, and these are the beautiful abstract. Everyone will like it. This will give you a kind of path to create a new research area. As I was listening to my colleague Xavier Moya about the electrocaloric, electrobarometric effect, all the things while I was traveling. So But all those, the area is quite new and quite good. Nanocrystalline, magnetoelectric, nanocrystalline. And then one paper that I found quite good in India is like that magnetoelectric by one of the student from Madras University. He has done marvelous job. Good. I'm happy to now we are also in India. Setup is there. They are doing good job. So. And so these are the abstract list of abstract. You can go through one by one, the 72 pages from various dignitaries, invited speakers or plenary speakers. So and this is the new essence for the webinar. I think this is good way we have interacted. So thank you. I think you can go one by one. So let us come to the point. Now it is there. So should I now again stop sharing the things? No problem?
Yes.
Yes,
Okay.
sir.
Okay.
You can stop it.
Okay. Thank you.
Thank you so much, sir. Indeed, this conference, it included all varieties of materials, starting from nano to bulk, covering all types of functional, indeed, we can say smart materials, which is the need of the hour. Thank you so much, sir. May I now request Dr. Balram Sahu, Material Research Center, Indian Institute of Science, the guest of honor, to deliver his address. Sir, please.
Yeah, it's. Do you hear me, madam?
Yes, yes, we can hear you, sir.
Yeah, what I will say, it's simply extraordinary. I congratulate Professor Parasar and all the organizing committee. And as I see, I mean, it's really international, and people from all over the world, not only from that's a few continents. So we have speakers from all continents and people watching all over the world. I'm also overwhelmed by the number of participants attending or listening to these talks, and they are benefiting. That's really, really very, very interesting. And it's a great success, I would say, Professor Prasar and his team. It's really, really overwhelming. And as you told, madam, it's, I mean, not only, let's say, materials or advanced functional materials, it covers, let's say, synthesis of materials, then their characterization, then applications in different devices. Also, not only the functional materials like, let's say, dielectric, ferroelectric, or piezoelectric and piezoelectric, it also includes many other materials in that. So, I mean, it's really, really broad. And the most important part that I want to convey here is the success of this conference. Had it been a normal conference, physically attending the conference, we would not have so many people benefiting from this conference. Now, you see, as one of our coordinators said, 4,000, 5,000 people are attending this conference. And if it is a physical conference, it would not have been so enlightening. And the other point is, instead of telling this a virtual conference, I would say it's an actual conference, but it's a digital conference. So maybe instead of telling this virtual, we say it's actual, but it's a digital conference. And by this process, and the organization of the whole conference was very, very good and extraordinary. Thanks to all these people who are supporting in this event. And I guess, I mean, all the participants and the students, whoever is listening, they are benefiting a lot. And that's what we need. And I don't know if this is the first conference, digitally international conference, but it's really very, very amazing, and it's really extraordinary. Thank you, Professor Parasar, and all of you within, I mean, from the KIIT University and whoever is helping in this conference. Yeah, thank you very much again.
Excuse me. I would like to thank Professor Sahu also for a continuous 5-hour questioning and answering to the young scientist researcher. I was muted that time, and I requested many times, probably I'll take some burden from him too, but then sometime it happens. But it was really, I cannot even 5 hours without any break. He was questioning and he was taking care of all the young researchers. Again, I would like to thank you.
Thank you. Thank you very much for this enlightening with this kind of speech. Also, you had a very nice speech. But I mean, by God's grace, I have this. I feel very well when I continuously enjoy this kind of new work, and people are presenting their best of their results, and it's really amazing. That's why I mean I was not bored. That's
actually you are enjoying that particular moment. That's why I was so delighted. You are enjoying each and every, and so really marvelous.
Yeah. Thank you very much. Thank you.
So thank you very much, Dr. Ashok and Dr. Balram Sahu. Continuous support. I can say before going to discuss the Young Scientist Award, because we have discussed sometime in the night, and in a session at 11 o'clock in the night, we have thought that can we do the functional materials. So Dr. Ashok told me, why not, we can start it. And then I thought we can find some good people in the world who can excite the students. So then he's given a list. And then out of so many lists, I given a mail to Javier Moya, and immediately he accepted. So this is great. You can say coincidence, you can say. God is giving I can say the COVID-19 made a beautiful, people are destroying, but I can say COVID-19 is a boon for the KIIT University, for us also, giving a new direction to connect the people. Otherwise, it's not possible to connect such kind of people, and all people without any disturbance, without any loss. So all credit goes to you, Dr. Ashok, who given the seeds of this conference. We are talking so much, but making a tree is another part. So seed is very important. The seed given by you in the night, and by your strong support, yes, we can go. Then we decided. And very quickly, within less than 1 month, I can say everything is done. Thank you very much. So it is time to the participant waiting for all over the world, morning to evening, to see the result. Before going to see the result, let I summarize the things. We have the very rigor condition for the Young Scientist Award, and this time we are going to give the e-certificate, but the money, we are not going to any kind of financial, but only we are going to give e-certificate, which they are going to keep in the lifelong, in the life. Even after death also, people are remembering the certificate. So certificate is never going to die. And this is going to create another momentum to the young scholar who, suppose not getting the thing, it doesn't mean that he is not working. We have kept certain parameters to measure. All people are very excellent to work, all people in different area, but we have kept some momentum to keep some other excellency, so that those students who are not getting, they should work hard, so that next year when we are going to organize, they have chance to get the award. And we have the different judge. One of the judges is Dr. Ashok Kumar, another judge is Dr. Balram Sahu, another judge is from Institute of Plasma Research, Piezoelectric Chaudhary, and many other people I don't want to disclose. Many people indirectly, they are sitting in the screen, and they are observing, they are monitoring everything. So I get many feedback, and then we have come to the decision to give the award. So it is my pleasure to have the declaring the name, and this name is I can say only for motivating the young students. So let overall, you can say we have not the first, second, third prize, but we have made some category about the fundamental and some application, this kind of things. So the first, you can say the Young Scientist Award. Overall, the first Young Scientist Award, I can say, goes to IIT Madras by Atal Bihari Soy. So have a big hand to give the Atal Bihari Soy this, and a pleasure to announce that he is also get this year the Humboldt Fellowship Award, nominated by Humboldt Fellowship. So it is this is coincidence that we are going to choose the Young Scientist Award, and this other part of the world also is recognizing. So great. Thank you for the Atal Bihari Swami, and all of us will get the certificate after this conference. The second, we have the prize. We have the two people in the group. So one is going to be the Venkateswaran Vivekanathan from the South Korea Nanomaterials and System Lab, Department of Mechatronics Engineering, Jeju National University, South Korea. And this is for the YS17. Earlier is YS5. You can see the program schedule. This YS5 is Atal Bihari Swami. This second is YS17, Venkateswar Vivekanathan from the South Korea. Another.
He's sharing the position.
And also this.
He is sharing the position with next.
Next, he's sharing the position with the YS11 with Sujay Kumar Ghosh. This is Ulsan National Institute of Science and Technology, South Korea, and he also both work on the some application part of the functional material. So congratulations to Sujay Kumar Ghosh also. And we have the third category of the prize, where we are going to have Anjan Kumar Jena from the IIT Hyderabad in the Laboratory of Nanomagnetics and Microscopic Laboratory, Department of Physics. He's also sharing the award with the Bhavesh Kumar Dajichi, Department of Physics, School of Applied Sciences, Kalinga Institute of Industrial Technology, Deemed University, India, KIIT University, India. So congratulations to Bhavesh Kumar Dajichi also from the organizer sides. And this time we have another award. We have the Young Scientist Award for the Women in Science. So because without women, nothing is going to be possible for the development of the science. So we have kept one award, Young Science Award for Women in Science. And you know, all of you, by the presentation and the question and discussion, you can guess who will be the Young Science Award for the women, and goes to Susmita De from the NIT Raipur, Department of Physics. Have a big clapping for all the women Young Scientist Awardee. And I can request now to give the blessings and the consulate and Javier Moya and the Gailin to this. So I request first the Gailin should give the conclusion to the all the Young Scientist Awardee. Professor Gailin. Gailin is the.
Yes, hello. Sorry, I was interrupted. So I am 9 again. What did you ask me?
Just to congratulate the young scientists that are awarded. Young Scientist Award awardees. You can congratulate them. And
yes, of course. So many congratulations to all the awarded students for these very nice works, for these serious and very promising studies. And I wish you good luck for the next steps of your career. Thank you and congratulations.
Thank you. Thank you, guys.
Thank you. I request Javier Moya to give the consultation to the awardee, Young Scientist Awardee. You can congratulate them.
Yeah, of course. Many congratulations to everyone who has been awarded. I'm sure it was difficult to select the winners. So, I'm pretty sure the work was very good. But many congratulations. That reflects on the work that you've done. And yeah, just best of luck for the next stages of finishing PhDs, postdocs, and then finding later some more jobs. So keep doing like you're doing, and yeah, hopefully you will strive even better.
Thank you. I request now to Atal Bihari Swami to give his views, and 1 minute or 2 minutes. Atal Bihari Swami, in a screen we have. You can talk now.
Hello. Hello. Yeah, we can hear you. Can you put on your video?
Congratulations, Atal. Now you can say something.
Can you see the video? Not yet.
No, he is unmuted. He is unmuted. Unmuted.
Sorry, video is not coming, I guess. So,
No problem.
yeah. So, thank you very much for noticing the work. I would like to, I'm feeling overwhelmed with this award. So, thank you, Ashok Kumar sir and Paras sir for organizing all these things. I would like to thank the organizing committee also. So, yeah, thank you. It's like a surprise to me.
Yeah, many congratulations.
Thank you, sir. Thank you, sir.
I request Smita De to share his views, her views. So Smita De, please.
Yeah, hello, can you hear me?
Yes.
Yeah.
Yeah, I'll not take much time. First of all, thank you all the organizing committee for recognizing my work, all the judges here. It gives me immense pleasure. It was really a surprise for me. And I think I would like to mention, which other people have not mentioned for this conference, like this is the virtual conference, or let me say digital conference, which was completely free of cost. There was no registration fee charge for this, and that is the reason I think many students have participated and have a chance to present their work. And what can be better, like we are all sitting safe at home and we can listen to the such eminent professors who are far away, like from Cambridge to South Korea to any parts of India. So it's a big I like to thank each and every one of you for arranging such digital conferences, and we wish like more you can arrange in the near future also, sir. Thank you.
Anjan Kumar Jena is here.
Hello, can you hear me, sir?
Yeah, we can
Hello.
hear you. Yeah, we can hear you.
Thank you all the organizing committee and judges for selecting me for the Young Research Award. And I enjoyed. I'm also surprising that I presented well, but I did not expect that I will get that one. But thank you all the member, because this I also thank you to my professor, my co-supervisor Dr. Jyotirjan Mahanti, who is helping me to achieve this. And also this work is going to be patented for a multi-level around device. And thank you. I have no word, so thank you.
Sujay Ghosh, YS11.
Sir, I have muted.
We can hear you.
Oh, okay, sir. I am very much overwhelming actually. So I'm working in UNIST, South Korea. So in this period, it's not possible to go anywhere to go conference. So I have just attended this conference because I don't know the publication is there or not, but to show the people that I'm continuing the research work and continuing interacting with the people, they are working in the same field. So I have just attended the Young Scientist Award application and presented my work. So it is unexpected that I have been awarded, and recently I've been awarded the Marie Curie Fellowship, but due to the pandemic situation, I'm not able to move. Hopefully the situation in Italy will be good so that I can move within this year. And thank you very much for the organizing committee for the selecting me, and the most thank that to present, to give me the opportunity, to give me the platform. This pandemic situation, we can't imagine that we can attend a conference like that. So very much thank you to all.
I request Banker sir from the South Korea.
He is not present, perhaps.
YS17, serial number YS17. If he is there, he can give a thought. And we have YS6, Bhavesh Kumar Dadichi, available.
Hello. Hello.
Yes, you can say.
Hello.
Yes, you are audible.
Yeah, thank you, madam. So first of all, I would like to thank organizers to notice my work and judges also. And personally, I was benefited by some important lectures that were delivered by Professor Balram Sahu, and some energy storage devices talk was very nice in this conference. And I would like to mention here that the zero cost benefit of this conference. And another important point that Balram Sahu has also mentioned, that Dr. Balram Sahu has also mentioned that the number of participants was benefited by this virtual conference is so huge, and that was not possible in a physical attend conference. So thank you organizers, and thank you judges for noticing my work. Thank you.
So I think Vivekanathan is connecting. I get the chat box message.
Yes. Yes.
Hello, everyone.
Yeah, Vivekanathan, now you can say something. Yes.
Yeah, can you hear me, ma'am?
Yeah.
Yeah. Okay. I would like to thank everyone, and particularly the convener, Professor S.K.S. Parashar, for his constant support, and he was very encouraging, and he was helping in all the communications regarding this conference. And I would like to thank the judging committee who recommended me for this Young Scientist Award, and I'm very glad to know that I'm one of the awardee that I received this award. Actually, I would like to convey that I have studied. I have did my PhD in Korea, and I'm continuing here as a postdoctoral researcher. And I recently received a Young Investigator Award from the Korean Research Fellow, and I have joined in that project. So I have been attending various international conferences in Korea, but there was a thing that I keep on missing. There are lots of conferences happening in India, and many of the professors in India, they were participating and giving their research, presenting their research in the conferences. But it was a thing that I couldn't able to attend those conferences. But because of this pandemic situation, now all these conferences are coming in the Zoom meeting and in online. So it was a great opportunity for me to attend to these various lectures happening, the conferences happening in India. And I feel very happy. I feel very delightful to listen to various talks. It's like this conference is particularly focusing on piezoelectric and ferroelectric materials, which I'm working in this field. So it's giving me a lot of support and much more idea about various materials and different ferroelectric materials and concepts. So I really want to thank the organizers and all the participants, those who are presenting their research in this talk, for their valuable sharing of their idea and concepts in this conferences. Thank you so much, everyone, for organizing as well as recommending me for this award.
So thank you very much. I congratulate you to all of the young scientist awardee. Now the challenge is going to you people to solve the problems of the whole world, so that the next generation people can get the benefit. Otherwise, whole world going to be have different challenges. We don't know the next challenge what will come. So the challenge is to you people on soldier how going to cope up to make the new revolution in the scientific world, and especially the science and the fundamental science and experimental science. The way you people are working, I am giving you consolation to all the young scientists body to go forward with the. This is one kind of, I can say, the momentum to work and give you acceleration to work more harder and harder, so that in this year or maybe within work, because the corona is not going to happen, finish going to this year, this will continue, right, according to WHO. So you can do some work so that the whole world going to benefit it. I can again tell you, because this is the big challenge. The Young Scientist Award, you will get it. We are going to send you within a couple of days the certificate by mail. If possible, we can have the. It is better to can send you the by digital mode. But I can again suggest you, if any young scientist awardee to work in the KIIT University to get the benefit of our laboratory and the facility, because there are different challenges here. I welcome you to visit here and do some work from your institute and KIIT University, make the next generation challenge to solve it. Thank you again from the organizer side, and a special thanks to our Ashok sir and the Dr. Balram and all the panel member for the rigorous, I can say. This is not a small task to have choose the young scientist awardee. It's a very difficult task. So they have given day and night discussion for the choosing the young scientist awardee. So thank you very much all the members for this who are someone are not available here, but they work very hard to find the best of a best. Only those kind of things are going to solve the problem of the world. Again, congratulating all the young scientists awardee and the panel member who made this successful. I can say without the young research scholar, this program is not going to be successful. So all credits goes to the young scientist participant, and we have your email, mobile, everything. So next program when we're going to organize, we'll give you a message to you and join for the next program. Thank you again on behalf of our organizing team. So I can request Dr. Bhaiba Madam to vote of thanks. Please, Bhaiba Madam.
Thank you, sir. So the journey that we started on 26th August 2020 has come to an end now. In this AFM 2020, we have total 12 sessions, 7 plenary talks, 14 invited lectures, and the speakers were from 5 different continents: Asia, Europe, Australia, Africa, and North America, covering the whole world. On this occasion of bidding goodbye, I would like to thank Honorable Founder, KIIT and KIIS, Professor Achyuta Samanta, Professor Hrishikesh Mohanty, VC, KIIT University, Pro Vice Chancellor, Professor Sasmita Samanta, Professor Sudarshan Nanda, Registrar, Professor Gyanaranjan Mohanty, Professor Pushpalata Pattajoshi, Dean, School of Applied Sciences, for showering their blessings on AFM 2020 to make it a successful event. I would like to thank convener Dr. S.K.S. Parasar and co-convener Dr. Dibyaranjan Raut for their timeless effort to make it a memorable event. I take this opportunity to thank organizing secretaries Dr. Sutanu Mangal, Dr. Gorki Saw, and Dr. Gopal Pradhan to provide all the technical support for which this virtual conference became a success. I would like to thank Dr. Sweta Padma Praharaj for her charming anchoring. I sincerely thank the organizing committee for their collective effort to make this event a grand success. I congratulate all the young scientist awardees for getting Young Scientist Award. I would thank all the session chairs for investing their valuable time. I thank all the invited speakers on this occasion for exchanging their scientific contribution. I would like to thank all the scholars, research scholars, students, and participants to make AFM 2020 a grand success. I would like to especially thank Dr. Ashok Kumar and Dr. Balram Sahu for investing their valuable time. At the end of this virtual conference, AFM 2020, I would like to repeat the words of last speaker of the session, Dr. Xavier Moya, that this century is the century of functional materials. I especially thank Professor Goylin and Professor Xavier for extending their time for motivating young research scholars. With these words, I would like to put down the curtain on AFM 2020. Thank you all.
Thank you and many, many congratulations. Thank you, Parasarji. Thank you. Madam, thank you.
Yeah, thank you all. Yeah, see you next time.
See you.
Okay, I think the organizers may stay.
Thank you very much.
Thank you.
Bye for
Thank
now.
you.
Bye.
Goodbye, everyone.
Bye-bye.
Goodbye, everyone. Stay safe in this pandemic period, and good night.
Bye. Mangal. Mangal.
बोलिए सर.
Thank you to making the. I know
ठीक
that
है.
you are have the
मैं
problem in the hospital,
मैं तो
your
क्वारंटाइन
support giving the wonderful.
अभी टेस्ट करवा के आया हूँ तीनों ने.
And for the participant, this information, the book of abstract in the website, anyone can download it.
And
The
also
book of
video.
abstract is already AFM 2020. The website is already there. Anybody can download.
And I think the certificates will be emailed. Is that correct? The certificates will be emailed, I think, to the students.
Yes.
Gorky, down the stream. Hello.
Yes.
Gorky, just stop the stream. YouTube stream.